Okay, time to start. So the next speaker is Avishay Gal-Yam. Might be ready soon.
Yes.
And he's going to speak about the diversity of supernovae.
Thank you. It's nice to be here. My tasked talk is about the diversity of supernova explosions, which calls for a review. So this is what I will try to do. And this review could take two forms. One is we can talk about the physics and the physical ideas. And the second is we can go to very small details and talk about many different subtypes of supernovae, each one having some specific property. And for my presentation, you probably guessed that I'm not going to do that. I hope you are relieved. So I will try to follow mostly ideas and less the details. I'll go into some of the details. And of course, if you want to ask me questions later, we can have an entire symposium on small lines in spectra of supernovae at some day. So this is the idea of the talk. It works very nicely. So this is basically a summary of this thing. We have physical models that we want to talk about, massive stars, binarity, we'll discuss this. And then I will try to connect this to all kinds of interesting and new things we see in observations. There are two basic tools that have been used for many decades to sort of set up the stage for the physical models for supernovae. One is the study of their environments, which galaxies they happen in. And this is from the TNS. These are all supernovae from the last, like the top of the list, so I think from the last couple of weeks. And these two are type 1a supernovae, so you can see they happen in elliptical galaxies, they happen in spiral galaxies. This one is a calcium-rich event, we'll talk about it in a second. So the fact that some events happen frequently in galaxies with very few massive stars call for some low mass, long-lived progenitor. On the other sort of method we had is actually looking directly at the progenitors, and this is one example like that from an old paper of mine. So here's a star in a galaxy far, far away, and then it exploded, and then we come back and it's no longer there. So we know this is the right star. In this particular case, it was sort of a million solar luminosity star, so obviously very, very massive. So the combination of these two things lead us to two types of models. The long-lived ones are wide dwarf explosions, which explain type 1a supernovae and probably calcium-rich events of their many varieties. And then the other big class is massive star explosions. And this is what we'll follow from now on. For wide dwarf explosions, the best story that I learned as a student and also taught the public in outreach talks many times, which is very beautiful, is that you have a white dwarf. It's accreting slowly material from some non-degenerate companion going up in mass all the way to the Chandrasekhar mass, and then it explodes. It's a fantastic story because Chandrasekhar mass is like fundamental physics. We calculate from basic principle. It explains why everything is the same sort of homogeneous class. It's really a very nice story. The only problem is that it's totally incorrect, and I have misled thousands of people in Tel Aviv for many years. So, and there are many arguments. I don't think this is a big argument now in the community that Chandrasekhar mass explosions do not explain most type 1a supernovae, but one I like is this argument from Sharon and Kushner, which basically look at two things you can easily measure for type 1a supernovae. One is the amount of nickel, radioactive nickel. This drives all the luminosity. It's a parameter that is, I think most people agree that you can easily measure and they get the same results. And the second one that they introduced is the gamma ray trapping time, which you can measure from the shape of the light curve, which I think also now people agree is something that is both physical and easy to measure. And the main thing with Chandrasekhar mass model is that you have nickel mass and you have inert mass. The nickel gives you the gamma rays and also some trapping, and the inert mass give you only trapping. And if the sum of those two is always the same, it means that the events with little nickel mass, which are over here, should have a long gamma ray trapping because there's little gammas and there's a lot of mass trapping them. And this cannot be avoided. All the simulations give you the same result, and it's just not what's happening. So if you look at type 1a supernovae, the ones with short gamma ray trapping are also the ones with less nickel. And this doesn't make any sense for the Chandrasekhar mass model, so they cannot explain the population. And then you have to have some alternative model, which is sub-Chandrasekhar mass, white dwarf exploding. Why should it explode? It's no longer this beautiful story about the Chandrasekhar mass. So there's probably some sort of merger, binary, triple, whatever. It could be a collision, which is very nice because it explains why the explosion happens, but maybe very difficult to actually produce the right numbers. Or there are these models with double detonations. Adam already has a question, and I will get with you in a second, where you create helium and create a helium detonation leading to carbon-oxygen. So all of these models could be. Just a second. All of them have challenges. Type 1a supernovae are very common. So about 1% of all white dwarfs explode. So you cannot have some sort of very fine-tuned model to explain all of these explosions. The trigger is hard to do. So sub-Chandrasekhar white dwarfs are basically stable. So you have to do something very strong to explode them. And then there is this diversity that we see here, right? Some of them make 0.1 solar mass of nickel, and some of them make almost 1 solar mass of nickel, and you have to explain this. Now I will stop and let Adam ask the question.
Just a quick question. On the more inert mass, the more trapping. The story I had always heard was that it also had to do with the temperature, the opacity, and the temperature dependence of the opacity. So that even if you had a thin layer, if you had all the nickel very close to it, it would heat it up a great deal, and that would create a kind of Phillips relation in a sort of classical still Chandrasekhar mass. Those were the Hoflick papers.
Right, but gamma rays are almost, they care very little about, all the temperature and density and even the composition. They don't really care so much. This is why gamma ray trapping is much more powerful than the total trapping. You are, for visible photons, for UV photons, you're totally correct. And the composition distribution within the ejecta is very important, and that complicated all of these things. And this is exactly why, for many years, this was sort of unnoticed. But once you look at MEV gamma rays, which are produced by the nickel 56, they don't care. Like the interaction with whether something is ionized once or twice, they don't care. I don't think Hoflich right now disagrees with me. Maybe he does. I don't know. But I think it's rather well agreed. Okay, and then there are other arguments against Chandrasekhar mass models. Okay, let me go on. The beautiful story does explain at least one subclass of type 1a supernovae, which are the ones that initially look like a type 1a supernova, but then it hits like a huge mass of hydrogen after a couple of weeks. And that obviously has to come from something that is not the white dwarf. So probably these are some sort of single degenerate systems, but these are a small minority. And then there are many other subgroups that have all kinds of weird things, and maybe people will mention them later on. Many of them have early bumps in the UV. Some show hydrogen lines in the nebular phase. Some show helium lines. Some have other evidence for late-time interactions, like becoming UV bright suddenly 3 years after explosions, all kinds of things like that. They all will have to be somehow explained. And my overall take of this is that probably there is some mainstream mechanism that explains most type 1a supernovae, which are, I remind you, very common in the universe. And then there could be multiple alternatives for the minority groups, which have all kinds of special binaries or triples or weird environments and all kinds of stuff. And my bottom line is that we actually understand none of them. Not the mainstream and not the peculiar ones. So there's a lot of work to do here, but also the observations are very strong, and I discussed this with Michael earlier on. Now there are like these huge samples now coming out of thousands of supernovae that nearby that have been observed quite well, and you can measure correlations and evaluate all kinds of properties, and I guess this will start to constrain these models quite strongly. Okay, now we move to massive stars. And in this, I sort of follow Selma's talk. Massive stars are very diverse. I listed some of the parameters, and Selma already discussed those and many others, complicating factors. So we have many sort of different beginning states for the explosions. And so there are, my personal goal for many years was to try to map different progenitors, stars that we actually observe, and types of supernova explosions. So we'll try to do a little bit of that. Here, I think we don't lack understanding of the basic things of the explosion mechanism. So Thomas reviewed this idea of iron core collapse, and it's predicted by the entire community, and we probably all agree about that. And then there could be alternative low mass models where the explosion happens, star evolves, and then there's electron capture in the core instead of ion core collapse, and then we can discuss a little bit how these two things will differ under different conditions. And then for very massive stars, the oxygen core becomes very hot at low densities and becomes pair unstable and explodes. This is also, I think theoretically, there's no disagreement about that. The only question is, does it happen in the nearby universe and how frequently? So the basic principles, I think, sort of are understood. And then for things like gamma ray bursts, probably we need some sort of internal engine that is highly spherical, there's a jet. So it probably requires some sort of a very rapidly rotating progenitor, which we heard from Selma, you can make, at least for some cases. And then for this case, there is an additional puzzle, which is what is left behind. We know some supernova remnants contain neutron stars, and we know some make probably black holes, and some of them are in binaries, and this is very interesting, so we'll try to touch a little bit about that. Okay, so here is what I will try to do for the rest of the talk. I will try to talk a little bit about what we can learn about the progenitor stars from the supernova side. I will try to show that there's finally some progress about binarity from the transient side, not from the stellar side. And then we'll discuss a little bit the identity of remnants, what we can see. Okay. Now, if we want to classify supernovae observationally, there are several sequences we can follow. And the main sequence is a sequence of composition. So we look at the supernova explosion and we determine what are the dominant elements that we see. And I think we can, from this analysis and also things Selma showed, that most massive star explosions come from what we call massive stars, 8 to 40 solar mass stars that explode via the core collapse of the core. And that some mass loss process explains the diversity we see. Some stars retain a large hydrogen envelope. I'm not sure if it's all of the hydrogen they had before, but many solar masses of hydrogen. And we see it in the spectra, and these are type 2 supernovae. And so that we understand. So these probably come from supergiants, blue supergiants and red supergiants and yellow hypergiants and all the varieties. But basically these are stars, massive stars that have a lot of hydrogen. Then a group of supernova shows little hydrogen and strong helium lines in the spectra, and probably these are stars that lost all or most of their hydrogen, and we call them type 1b. And then in some cases, the helium is also not seen, probably removed, and we call this type 1c. And this has been known for many decades and explains most observed supernovae. Okay. Then there's another sequence. Sorry, before that. And then there are intermediate types. So type 2b have more hydrogen than type 1b, but less hydrogen than type 2s. And there are a sequence of intermediate objects that sort of bridge this gap quite nicely. Probably there's a similar sequence between type 1b and 1c. And all of this is sort of to be expected. A second sequence comes from the fact that massive stars lose a lot of mass. And Selma said type 2 supernovae are boring. So we had in Garching last week, we had an entire 3-day meeting that Selma basically hosted, even though she wasn't there. On just one, actually, eventually it became sort of 2 type 2 supernovae, so it wasn't boring at all. But basically the bottom line from there, which was also already mentioned, is that these exploding supergiants, at least half of them have nearby circumstellar material between 10 to the 14 to, let's say, 10 to the 15 centimeters from the sun, from the star. There's a fraction of a solar mass around type 2 supernovae. This is hydrogen, and then around other types of supernovae, higher mass materials, and they create a sort of interacting supernova sequence. Some supernova interact with hydrogen, some supernova interact with helium. These are type 1Bn, and recently there's this type 1Cn group that interacts with carbon oxygen, and they can all be somehow still understood as massive stars that lost some of the mass, and some of the mass is still lying around, and I think probably this requires some sort of binarity because the amount of mass is large and the exploding stars are themselves probably low mass, so they cannot be very massive Wolf-Rayet stars, at least not most of them. And then there are extreme cases that class has been studying for a long time, type 2N supernovae that interact with a lot of hydrogen, and this interaction carries on and on and on and on for many years, and these probably have to come from massive stars that lose a lot of hydrogen continuously over a long period of time. So it's not just around the star, but it extends to very large distances, certainly above 10 to the 15 centimeters. Okay, and then as our observations, especially at early times, improve, I will touch on that a little bit more, we find more and more supernova types. So this just never ends. And Steve is here and is now writing a paper where single-handedly is going to define not one new supernova class, but actually 4. So this is a supernova that whose spectra is dominated by silicon and sulfur. So because of that, according to the spectroscopic sim, it's a type 1En supernova. So it's silicon and sulfur interacting with silicon and sulfur. So even though this is the one we see, in order to put it into the book, you have to define type 1E supernovae, and also 1D and 1Dn, we have to keep names for them because they might appear later. So in the same one paper, there will be 4 new supernova types, even though only one of them is detected. Now, in principle, it's a nice cartoon we have here, so maybe we can extend it. Okay, so remove these 2 things, and we have the silicon layer interacting with silicon wind, but I think it's totally unphysical because the silicon layer is actually formed so shortly before the star explodes that to assume that some conspiracy existed that everything above it is removed and it manages to put some wind around and then interact with it sounds terribly contrived to me, almost impossible. So it's probably some sort of other thing, and we are now working on thinking what this could be. So this will tell you a story about this, maybe, I don't know, in a couple of months, and then you can decide if it's a nice story or not, and there will probably be other stories. So whenever I make these figures and I think, okay, this is the final form of the figure, nature intervenes, and we find more and more things that we have to add on this figure. So this is the probably 3rd or 4th version of this particular figure I had to make, each time adding a new spectrum. So the massive star arena is very diverse, right? There are many things. I only showed a few of them. Another sequence that exists, and many people here have been involved in that over the years, is a luminosity sequence. So for many years, supernovae were sort of capped here, which is type 1A supernovae were known to be the most luminous class of supernovae. Type 2Ns are sometimes a little bit more luminous than that. And then we started seeing these very, very luminous supernovae, much more luminous than the regular ones. They are very rare. Typically, we see them at large distances. And we call those superluminous supernovae. There's a threshold I put here over a decade ago, which was totally fiducial. And then since then, I think we now know for at least for superluminous supernovae of type 1, the ones that don't show hydrogen, there's probably a physical border between the superluminous class and the regular class around -19, -20 G magnitude. For the type 2s, I'm not sure if there is if it's a continuous sequence or there is a border. But the interesting thing about these luminous supernovae, and by the way, GRBs make also luminous supernovae, which are sort of in the middle here between, cover the range between low luminosity type 1c supernovae and the superluminous ones. Interesting things about superluminous supernovae. Some of them have such large energy budget that they really challenge the typical neutrino models. You know, Thomas told us that they can make 10 to the 51 or several 10 to the 51 ergs, but some of those require 10 to the 52 ergs. I mean, this is really hard to make. So obviously they require something else, something additional. And the extreme cases, and again, Steve just published the best one, actually fit per instability supernova models that naturally make a huge amount of radioactive nickel, and you can just power a very powerful supernova in this way. And Ragenhild, which is also here, published the previously best example, and I think both of them are probably, in my personal opinion, both of them are right. So I think, again, as an observer, I sort of give up with this object. We brought the best per instability supernova in the local universe. We put it on the table. Now it's the theorist business to convince themselves whether or not it's the right one. We cannot do anything better than that. If this is not convincing enough, I give up. So, yeah, so this supernova has a lot of nickel, and it also has some interaction that makes these bumps, which I think you sort of have to expect if you think about a progenitor that was 100 solar mass or more, probably much more. Okay, so, and then low metallicity, high redshift universe, there are probably more numerous and maybe even more convincing examples of this. Moving to shorter timescales, we find many interesting things. I cannot review all of the things we do because it's very interesting. One thing that Anna will cover, and I will not talk about therefore, is the fast transients with typical timescales of a few days. So there will be a totally entire talk about that. But also short timescale supernovae are quite interesting. Some of them have fast rises, fast declines. They probably require some sort of different mechanisms, right? They cannot be just diffusion powered nickel explosions. So this is actually quite interesting. So new things. One thing, I promised binaries. So I was really happy to see this. So Ping Chen published this paper in Nature, and there's an additional paper by Moore et al. And this is the first time we see a supernova that came from a binary progenitor with direct evidence. The direct evidence are these periodic bumps in the light curve. They have the same structure. We see them over multiple colors, multiple telescopes. They're really real. And they are accompanied by an H-alpha line that has a Doppler movement that is in phase with the photometric variability. So it's really like observing a spectroscopic binary star that is moving, and we see the stars pulling on each other. So this was a type 1c supernova that was followed by this extended phase with this binary or this periodic activity. And then what Ping found was that it became actually gamma ray bright in GeV gamma rays from Fermi during this phase, and then faded away. It's a 5 sigma detection. So to me, it looks like what we are seeing here is really direct evidence for a supernova in a binary system where the binary survived the explosion and formed a compact object, which must be the source of these gamma rays. So there's a nickel explosion followed by this interaction phase. I don't know if the remnant is a neutron star or black hole, and I think here we weren't prepared to this thing, but I think this is one of the best options we have to determine whether the remnant is a neutron star or black hole, because we have access to direct electromagnetic radiation coming from the surviving remnant. So now we only have this single gamma ray detection, and I'm not sure it's sufficient information to determine what it was, but to me it sounds like this is the way to determine eventually if these things make black holes or neutron stars and when. Another one thing that I want to, I'm sort of guessing Anna will cover this, but there is also evidence for late time flares coming after fast transients, which are also types of massive star explosions in my opinion. And this also must come from the binary companion. I'm getting there. So I think we're finally stepping into this field of seeing both the explosion and being able to constrain the properties of the surviving remnant, black hole or neutron star. I think this is very exciting, and this is totally new. It's like two years. The supernova we studied for last week in Garching offered an interesting option to utilize this theoretical argument that Udi and others made, which relates between something that is relatively easy and nice to measure, which is the energy multiplied by time integrated, which it's an integral property, so it's nice, it's bolometric, and it's related to, if you have a massive supergiant explosion, the ejected velocity, which we can directly measure, the radius of the original star, and the ejected mass, and this is something we can measure. So for this object, we measure it very well. You see this, we can really derive bolometric luminosity because we have coverage in all wavelengths for, a long time. And we can also measure the ejected velocity, and because there are pre-explosion images, there are limits on the exploding star radius. So we can derive the ejected mass, and we can do this calculation. Okay, you can see it over there. There's the zero age mass sequence of the star, minus some mass loss that happened before, minus the ejected mass that we can now measure, should give you the remnant mass. And for one outlier measurement, you get a negative remnant mass, so I guess something is wrong with that measurement. But for everything else, the remnant mass is high. It's much higher than a neutron star. So from this argument, it seems like maybe at least this particular supernova seemed to have made a black hole, like a 5 solar mass remnant. So I think it's interesting. There are all kinds of caveats to these sort of studies, and it's the first time we did this, but you can do it. Actually, for nearby type 2 supernovae, you can do it again. There's no reason why not to do it. Okay, yeah, this is the supernova. So to summarize this thing, before I go very quickly over some other things, I think from observations of supernova, we are close to providing for massive stars a census of stars with estimates of radius, composition, some idea about metallicity, from late time observations, ejected mass and nickel 56 masses. And this is a good benchmark to match models, both the models that Selma showed and the models that Thomas showed. We begin to probe binarity directly, which I think is nice. We begin to say things about the remnants. The explosion energies are not low. They are sort of 10 to the 51. So I said challenge to models, maybe not. Maybe it's consistent with models. One thing that is very clear that exploding stars begin to be somehow unstable, either have eruptions or enhanced mass loss or enlargement of the radius like the Fuller and Tsuna models. Whatever it is, months before explosions, massive stars change. And in the meeting we had in Garching, Nathan Smith pointed out, I think he's correct, the progenitors that we have to assume to explain type 2 supernova explosion, at least half of them, do not exist in our galaxy. There are no supergiants that look like the ones that we determine we must be. They have to be very large. So something happens. It doesn't have to be a violent eruption. Maybe the stars slowly expand, but they expand to become different from the ones we see. So I think it's a big clue about stellar evolution, and also maybe you need a different initial condition for the explosion simulations. I think similar advances are going for white dwarf explosions. As you can see, I didn't have time to review them. What's coming next? So I think relating to the TNS images that was here before, wide field is the key. So ZTF did so great because it had the widest field of all. Now we have an instrument in Israel that is even wider, last. So this is it. Eran Ofek and Sagi Ben-Ami are running it in the desert. And I'm putting here this is a supernova we observed like 2 days ago. And this shows you 3 images, but the supernova was actually detected in 6 stacks. Each stack is 20 images, so we have 120 images of this supernova. And every night, and we can do this for the entire sky, basically. So it's going to be very powerful, providing both detections and time-resolved information during each night. The number of events is huge. Spectroscopy is going to be very important. So we were involved in building SOX, which will go on the ESO telescope NTT and start being available to the community in about a year. And this would provide classification spectra at very high quality. It's a very efficient instrument. Talk to me more about this if you want to learn. And coordination is very important. I'm showing here the ZTF, slide. You find things here. Maybe I should do it here. Okay, you find them here. You follow up here and there. And actually, this worked very well for us because we also had Gemini in Hawaii, which gives you 2 more hours to get your act together and get the spectrum. And I think now on the other side of the ocean, we will probably do some similar things with Israel and La Palma. And I think globally, we are moving towards coordination of discovery and follow-up basically throughout the entire planet. And this is what it gets you. And then finally in space, Ultrasat is a wide-field UV mission that will be very, very strong source for very young transients, supernovae at age hour, kilonovae from GW events and so on. Expected launch date is end of 27, and it will, I think, really revolutionize everything I showed you this far. This talk will be very different 2 years after the mission is in space, and I will stop here.
Thank you very much. Okay. Questions?
For the binary stars that you mentioned, you indicated that you can find them both with light curve and Doppler shifts in the lines.
Yes.
If you have enough spectra, and I don't know how much enough is, will the Doppler shift method be easier to look for that?
Interesting question. So these are X-shooter spectra, pretty high resolution, and you sort of need that. So you need many spectra with decent resolution. You don't need, X-shooter is a bit of an overkill. You probably can do it with, I don't know, Keck, LRIS, but not maybe the lowest resolution. So it's possible, but I think the light curve will still be, this is probably simpler, easier.
Nancy.
Oh, I think
but there's a chair. He's the boss.
Nancy.
Congratulations on the first supernova images from last. I was just wondering if you could tell us more. Is it all 48? When will you have a last discovery alert stream?
Good question. So I got from like a fact sheet from Iran that the things I should say, and I forgot most of them. But anyway, okay. So last operates within a structure, which you can see here, it's totally open, but of course during the rare windy or rainy conditions we have to close. And this structure was giving us all kinds of pains, and basically it's the main reason that we haven't been working robotically now for a few months. And it's fixed, and this fix seems good, finally. So we are now starting remote observations with an on-site support person just in case something breaks. And within a few months, Ran will trust the system enough to go fully robotic, and then we have a better structure coming up at the end of the year. Also until 20, we have all the 48. This is 32 telescopes. We have all 48 of them at Weizmann Institute being prepared, and we'll probably install the rest. Also by the end of the year, we are now doing the mechanical integration with the mounts. Alert stream. So we have a pipeline that is running, scheduling, collecting all the data, reducing it. The image subtraction pipeline, this is the result of that, is running. As you could expect from Iran, it's extremely, it took a long time to develop, and it's extremely efficient and good. So the purity, the number of real transients out of 8 sigma detections is more than 99%. So in principle, we don't need anything. We can just take everything that's detected and put it on the TNS. It's going to be better than most other surveys. So this supernova is, I don't remember, a 45 sigma detection or something, because there are so many images. So it's coming there. There are still some things, because everything has to be perfect, as you can guess. So it runs several algorithms, both to find the events and then to reject moving objects in all kinds of sophisticated ways. But it's very clean. It's a very clean data stream. So I think by end of this year, we should have everything. And we will probably not have an alert stream. We'll just put them on the TNS immediately, because we have no false positives. Very few of them.
What's the limiting line?
For a single image, about 19. And we typically have 6 images per night. So in principle, if you stack all of them, which currently we are not doing, you can go deeper. But I think 19 is sort of where it's going to happen. On dark nights, it's even better. Actually, it's 19.5. We have a little bit more light contamination coming from some activity in the south of Israel. Who knows? But hopefully it will go away. So, okay. Yeah.
Wow.
Okay. Yeah, Adam.
I'm embarrassed to be asking you this question, but why do type 1A supernovae mostly blow up at the same luminosity?
Well, very cool question. So first of all, what you said is sort of a misconception, right? If you look at this figure, okay. So the amount of nickel here is actually almost linearly proportional to the luminosity, and it changes by a factor 10. So there's actually a range of luminosities for type 1As. However, when you run a survey like ZTF and you are flux limited, you find mostly the luminous ones, and these are indeed very homogeneous. So you find, let's say, the upper 20% in luminosity, but there's actually a big range below that, which typically you don't care about because they don't appear in surface.
But even locally, we are dominated by what we would call normal type 1A supernovae, which have a pretty narrow range.
Yeah.
But I was asking the question, so why do they have such, why is there such a narrow range then of what we see even locally? I mean, yeah.
So first of all, you are asking me this question. But let me venture a reply. So I think the fact we are dealing with white dwarfs sets the sort of field, right? So the total mass is around 1 solar mass. The amount of nickel, as I said, is capped from above at 1, and typically is less than 1. And it's probably capped from below by the fact that the ones that make very little nickel, we just don't see. And we don't find them. They could happen, but we just don't see them. So your ballpark is more or less like a few tens of solar mass of nickel within a total mass of around 1. And that gives you a short range of luminosities. I think that's the main thing.
But what homogenizes the explosion to occur around 1 solar mass then?
And not other masses.
Yeah, are you saying it's a double degenerate where the mass function peaks at half of that? And
yeah. So most massive stars are 0.6 solar mass or so. Take 2 of them with some efficiency, you get 1.
Easy.
No, if you look at it, by the way, if you look at the mass function of white dwarfs, there's a big peak at 0.6, and then there's a small peak around 1 point something, which is probably merger products that didn't explode.
Okay, Arya.
So you mentioned, congrats on the last thing. What's happening with the fast thing, the CMOS thing? Is that going ahead?
Yeah, so, okay. So it could be operated. It's an older system. Now we wouldn't have built it the same way we built it at the time. We are using it sometimes to do follow-up. We are not doing a survey. In principle, with that system, you could have done a survey at 100 hertz, right? Exposure time of fraction of a second. But the data volume that is generated by this system is such, even for last, we have to do most of the processing on site because it's located in a small kibbutz, and transferring the data to Weizmann requires more than the entire communication budget of the entire community, much more. And for fast, it's totally impossible. So basically, you have to go down there with disks and take them up. So doing a survey, I think, is unreasonable. We can do it did a survey for occulting culpable objects. I don't know if you follow the results are out. But I don't think it's going to run in survey mode.
What about the two recent supernovae within 7 megaparsecs? I mean, could you follow those or something?
Yeah. You could have. I think. Yeah, you could. We didn't. Oh. One of them is in the south, but the other one, yeah, we didn't do it with fast. As I said, it's very clunky. It's hard to operate. Last can give you continuous coverage of a supernova like that with a cadence of a few seconds. If you want to do a sub-second, yeah, we can do it, but I'm not sure we will. It's too much. We are concentrating on actually building a spectroscopic facility, which I will not tell you about now because it's unfair. But ask me about it later.
Okay, any more questions? Yes, Thomas?
I had two questions about this supernova which you discussed in Garching and which I didn't attend the workshop. First of all, the explosion energy, and the second is how can you be sure that you have good estimates of the mass loss?
Oh, no, yeah. Okay, so let me go here. So this budget here that we are discussing.
Yeah.
So for that particular supernova, which is so nearby, the mass loss is actually rather well constrained by observations. There are X-ray observations and radio observations, not upper limits, detections, that actually constrain. Now we are getting to 10 to the 16 centimeters. And there is circumstellar material, but we can estimate its mass, and it's low. It's not certainly below 1 solar mass. And so adding 1 solar mass here will not change the question. Now, if there was a lot of mass loss in the past, so I don't know, well, at the beginning of the red supergiant phase or something like that, that could solve the problem, but that requires a significant change in mass loss models for massive stars. Not because the end states are poorly constrained. So everybody says, okay, at the end, maybe there's enhanced mass loss. But to actually avoid this thing, you have to have enhanced mass loss throughout the red supergiant phase for, I don't know, thousands and thousands of years at least, probably more, to remove several solar masses. So yeah, maybe it happens, but again, it doesn't happen for other stars in our galaxy. Not even, you know, there's this VY Canis Majoris, right? The one that has 10 to the -4, but that star is much more massive than this one. It's not similar. So, and the rest are much less.
So what's the ejector mass and the explosion energy?
The explosion energy is sort of regular. I don't remember exactly, of order 10 to the 51. The total ejector mass is 7 or 8, something like that. And the progenitor mass has to be above 12 or something like that. And the gap, that's the gap. Yeah.
Okay, I think we should go on to the next talk. And that's by Dan Perley, and he's going to speak about the complete survey of the catastrophic universe, science with 10,000 supernovae.
It's a discovery, but supernova was known before. It wasn't pointed at this location. Yeah.
All right, thank you, and thank you for the opportunity to speak here. So if you go to the conference website for this meeting that we're at, you're greeted with this all-sky representation of supernova discoveries at some point in the recent past. And what you can see right away from this is that there are a lot of supernovae right now. There are thousands, tens of thousands of supernovae that have been recorded. And so the purpose of this meeting, in a sense, but especially the purpose of my particular talk, is what is good about having just lots more supernovae? You know, is it useful to have 10,000 when we don't necessarily understand, even if we have the greatest possible data on one of them, everything that's going on? What do we gain by going to these large samples? So another way to represent this is in terms of a plot with the time. This is another plot that you will see in lots and lots of different talks, going back to the early history of supernova searches, the first serious discovery searches done by Fritz Zwicky and other people. mid-20th century, and then this massive increase that's going on right now. So again, what do we learn from lots and lots of supernovae? Many of the talks that you'll hear today have to do with how discovering more supernovae expands our notion of what supernovae do and what they can come from. And there is a precedent for this that goes back even before the understanding of what supernovae were. So if you imagine yourself in prehistory, there was the night sky was filled with stars. Most of them were not doing anything. Most of them were not changing. And then someday somebody in some civilization, this happened across many civilizations, noticed that there was a new star that had showed up. And this, if you're thinking deeply about the cosmos, that one out of 10,000 stars in the night sky has suddenly changed your notion of what a star could be. Now, of course, the people did not know what that supernova was, which we do now. But that was the beginning of the understanding that if you collect a lot of things, if you observe the sky for long enough, you discover new classes of phenomenon that broaden your notion of what is going on in the universe. And this has continued on throughout the history of the field. The distinction between novae and supernovae, the distinction between type 1 supernovae and type 2 supernovae. Each one of these started by just collecting lots and lots of things and noticing that one or some of them were different. And this continues on to today. And you'll hear many, many talks about some of the curiosities that have come up in recent years, which have expanded our view of supernova demography and what massive stars and other stars can do when they explode. Nevertheless, when you're thinking about large samples of supernovae and focusing in on one of them and going at how it's weird, sometimes if you're a skeptic, you may feel that this is not perhaps making as much use of your large samples as perhaps you could have, that you're finding this curiosity and that curiosity, and maybe we'll figure out what those curiosities really are in the future. But okay, what about the normal things? What about the large populations? And so in this talk, I'm really going to focus on what can be learned, at least in principle, from large samples of sort of better understood classes, because we can still learn a lot even if we're focusing in on just normal 1As or just normal type 2s by increasing our samples, and especially if we increase them in a systematic way. In particular, things like rates, things like bimodalities, trimodalities, classes, groups, phase space. If there are predictions and someone says this kind of class event should exist, if we don't find it, we have to be very systematic and we have to collect lots of data to actually say that that thing doesn't exist in nature, as well as connections to things like host galaxies and environments and ages of the progenitors and anything regarding where systematics are important, like doing cosmology with supernovae. Large samples are helpful, especially and particularly if you're able to gather this sample in a stable, long-term way with good selection methodology. So this is where the specific topic of my talk comes in, which focuses on the efforts to do exactly that with the Zwicky Transient Facility. Most of you in this room know what this is. It is a survey that's been going on for 7 years now using the storied Palomar 48-inch telescope over here in the background of this picture, which has a helpfully great combination of abilities, a reasonably large mirror so that you can go deep, and a very large field of view camera, which allows you to go wide. So it's deep and it's wide at the same time, and so this has just been great for finding lots of things, and particularly lots of things at the bright end, where you can actually get spectrum of them. And as part of this project, there is a fully dedicated, low-resolution spectrograph called the SED machine that's been operating since the start of the project, getting spectra of all the bright things in the survey. And so about 1 hour on the spectrograph can get you at least a classification so you know what things are. So over the years, we have developed a methodology to do this uniformly for all the transients that are bright enough. Things are found by the survey. It dumps a public alert stream to the community. We run that through a software filter to remove the things that we're not interested, like the asteroids and the variable stars and the cosmic rays and everything else. We scan those every night. This is slowly being automated as well, but for the time being, we're still looking at the choice candidates by eye. The ones that are bright enough, we assign for spectroscopy. We classify them if we can, and if we can't, we keep reassigning and reassigning and reassigning until we get it. And this gives us lots and lots of supernovae. So, so far, we are closing in on 10,000 classified supernovae brighter than 19th magnitude, including lots and lots of things of various types and classes, in which I will not go through all these numbers here. I just wanted to show lots of numbers to impress you with numbers. Perhaps the more important numbers that I'm for this talk, though, are the numbers on the right. These are the numbers of supernovae that are brighter than 18.5 magnitude, which is sort of our completeness limit for this survey, passing the selection cuts of happening in fields with good cadence and not about to set and not about to rise and not about to be wiped out by the moon and not when we're about to have 2 weeks of hardware maintenance. These are things where we not only have spectroscopy, or it's not only bright, but we also have good the ability to get good photometry. And for that subset, it's still a large number and it's nearly complete. So only 6% of the things in meeting these criteria don't actually get classification. So we can say pretty confidently that we're detecting everything pretty well. Now, the other thing that a survey like this gives you is not just lots of bright things to follow up and get a spectrum of once, but it gives you the light curves. And so this is a tiny, tiny subset of the light curves and 2 filters, G-band and R-band, for the things in the survey. And that's just great to look at because we all love light curves. But you can also make measurements on these light curves. And so, for example, here are the 3 filter light curves of one particular transient. And you can do various things with this depending on what class you're interested in. But if you just want to start with the absolute basics, you can just say, okay, what was the peak luminosity in one band, let's say the G band, and what was the time scale? Okay, so we'll just start with those 2 numbers and plot them. And you can already just learn a lot. So this is a plot of all the bright transients in ZTF, simply plotting the luminosity versus the time scale. And you can see right away that nature likes to put things into groups. There is an aftergroup up there from relativistic explosions. There's a novae group at the bottom, which are explosions that don't destroy a whole star. They're just eruptions on the shell, as we know from Astronomy 101. And then there's this gigantic class of supernovae, which to really get into detail, you have to start doing the spectral classification to see what has hydrogen, what doesn't have hydrogen. There's lots and lots of interesting structure going on in each of these groups, which I will not have time to talk about today. Instead, I'll just mention that all these things and how the trends are and whether they slope upward or downward in each of these classes reflects the impacts of all sorts of interesting physics. And with large samples of these objects, we can gain insight into how those physics affect the explosions and what that tells us about the stars that produce them. So instead, what I'm going to choose to talk about is just a small subset of these classes, if I even are able to get through them, and how we can learn some fundamental things with large samples. So the core collapse supernova rate overall, a little bit about type 2s and type 1 BCs. There's other things I could have talked about that I won't have time. Type 1As, Avishay helpfully has described what I would have described there, what you can do with large samples and connect that to white dwarfs. So let's start with rates. So as you heard in Thomas's talk, there are lots of explosion models out there, and historically, and still to some extent now, lots of those explosion models fail to actually destroy the star and produce a supernova of the type that we normally observe. And so a big fundamental question in the field is, could it be the case that some, many, most even, massive stars actually don't produce supernovae? They collapse more quietly and we never see them. And so one way that you can address that is with this simple method that's mentioned on the bottom left there, which is, do we find enough core collapse supernovae compared to the predictions of all, the star formation rate in the local universe and counting all the stars more than 8 solar masses and determining the supernova rate from that. And so we can now do this pretty well because we have a very good completeness. We have a very good completeness to bright things, which means we have a very good completeness to the whole supernova luminosity function out to a certain radius. So we can use that. We can use our survey to construct luminosity functions, the number of supernovae as a function of luminosity, and then we can integrate that to get a rate. And so these are the current rates right now from the Zwicky Transient Facility for core collapse supernovae, the population that's relevant here. It's about 9,000 per cubic gigaparsec per year in the local universe, redshift of 0 to 0.1 or so. So how does that compare to the predictions from star formation? Well, these predictions are uncertain because there's lots of assumptions. But if you take the star formation rate, you run it through an IMF, one prediction for the number of core collapse supernovae you should get is 17,000 per gigaparsec per year. So it's about double that. So there is some tension here. It's not strictly an inconsistency, but it is at least suggestive that there might be a missing population, some of which could be just obscured, but some of which could be direct collapses to black holes that we don't see transients from at all. So this is an interesting thing that continues to motivate work in this field. Okay, another interesting aspect, which Avishay already alluded to, is the nature of mass loss towards the end of lives of massive stars. And so we know from some specific examples, including 2023 IXF, this wonderful supernova from last year, which I show a spectral sequence here, that when the supernova explodes for a brief period of time, UV radiation from the early phases of that explosion ionizes a lot of material and produces these super bright, short-lived emission lines. And that material has to be very close to the progenitor star because it vanishes within a few days. And this requires, of order solar mass of material on a radial scale of 10 to the 14 centimeters around the star or so. But we don't see this always. We only see this sometimes. And an important question is this really common? Is this all stars? Is it a tiny subset of stars? So how common is it really? So one thing that we've been using ZTF to do, and this is largely work that's done by my student K. Ryan Hines in the audience, is to try to do this photometrically. Because photometrically, there are also signatures that don't require spectroscopy, which is quite difficult to get on the early phases which you needed to determine this. Because if you look at light curves, if the light curve rises fast enough and becomes luminous enough, you also need circumstellar material in about the same radius to explain that. So it's possible that we can address this with light curves specifically. And with ZTF, we have lots of light curves. We can use those light curves to estimate approximately the progenitor mass. And what we determine is that majority, perhaps a large majority of all type 2s in the universe, and therefore all red supergiants, the progenitors of type 2s, at the time that they explode, are surrounded by, of order 0.1 or so, 0.1 to 1 solar masses of material. So this is not just a tiny subset of obscure stars undergoing some weird binary channel. This is the majority case, or nearly the majority case, of red supergiants. So this is something that stellar models have to understand, how you get that material on that time scale to those radii. Okay, then the final thing I will talk about is on type 1Cs. So Selma talked a little bit about timescales and progenitors of type 1Cs. And I will say, at least when I learned about supernovae and massive stars, I was told is that type 1Cs come from Wolf-Rayet stars. And if you look at the mass distribution of Wolf-Rayet stars in our galaxy, they tend to be fairly massive stars, which is not surprising because massive stars have stronger winds, and the stronger winds help you strip the star and get rid of that hydrogen and helium. But you're still left with quite a bit of mass even after that. And if those are the stars that are exploding and making the type 1Bs and type 1Cs, you would expect the ejecta masses coming out of those type 1Cs to be pretty significant. Additionally, the explosion modelers tell us, okay, I'm no expert on this, but if you look at some of the papers, they say that these explosions of these should not actually produce that much nickel, so much less than a type 1A supernovae. So they should be long, they shouldn't be very luminous. Basically, that is not what we see overall, at least for a significant fraction of the population. A minority, after correcting for volume effects and detectors and so on, exceed this luminosity limit where it's sort of too high for what the explosion models should say. So this is work that Jesper Solerman here performed a few years ago using the Bright Transient Survey sample and found that a significant fraction of type 1Cs do exceed even normal type 1Cs, no weird spectra going on. No strange light curves, normal light curves, just on the high luminosity and the luminosity function. They seem not to be explained well by the explosion models as they exist and seem to require something like an extra magnetar or some other form of energy injection to explain them. And additionally, more fundamentally, in work going back even before ZTF, but ZTF confirms it, is that if you take the ejecta masses that you measure from the light curves of type 1Cs and spectra when you have them, it's much less than you'd predict from the Wolf-Rayet population. So if Wolf-Rayet stars are exploding, they're not producing the 1Cs that we see. They're producing something else, which we don't really see the majority of the time. And the 1Cs that we do see must come from some lower mass, more stripped, perhaps some binary channel, and not massive Wolf-Rayet stars. So now what are they? Well, perhaps a clue comes from some of these rare interacting transients, these 1CNs that Avishay mentioned. They seem to be consistent with being much more massive stars. And interestingly, when you see those explode, if you follow them to late enough times, the luminosities are very, very low, suggesting that those massive stars actually don't produce much nickel. And when they explode, they perhaps are actually collapsing primarily to black holes rather than making luminous explosions at all. It's just one possibility, but it suggests, again, together with the IMF, together with the observations of normal 1Cs, that there might be still, even with these giant surveys that we're doing so far, some obscure, rare, hidden pathways of the deaths of even fairly common classes of stars that we're only starting to pick up on. Okay, so to summarize then, since I'm running out of time, we now have the ability to monitor the night sky in a complete way down to fairly deep limits and gather very, very large samples of supernovae, which are broadening our view of the ways that stars can die and also giving us new insight onto so-called common classes of objects and leading to surprises, such as the discovery that type 2 progenitors are surrounded by unexpectedly large amounts of material at the time of death, and that type 1Cs do not seem to be coming from traditional Wolf-Rayet stars and may be illuminating interesting ways of deaths of these most massive stars. Thanks.
Very much. Okay, questions? Selma.
I like your little ejecta masses for the 1Cs, but I don't know how unbinary strips all the helium off. Well, not only me, I think that's still an open problem. So it's.
I also do not know how a binary strips the helium off, and if you don't know, then I'm particularly concerned about the fact that there's no way to do this. Particularly as often as we do. I didn't mention the total rate of 1Bs and 1Cs in my slides there, but we can calculate that as well. Let's see. Yeah, you can integrate that, and you get it at 20% of the type 2 rate. So you have to do this a lot. For every ordinary red supergiant in the universe that explodes, for every 5 of them, there has to be one of these weirdly stripped lower mass progenitor stars that also explode. So this is definitely a challenge.
I know ways to do it, but not at these rates.
Yeah.
Okay, more questions? Is there any way to, these which disappear into black holes or something like that? Is there any way of?
Well, yeah. So that's, that's sort of where I think things are pointing, at least for the stars, the Wolf-Rayet stars that are massive. We don't really see a supernova corresponding to the predicted properties from when you collapse something that massive at the rates that I think that we should. These things like these 1CNs might be really, really super special cases where the star might be rapidly rotating and there might have been a ton of mass loss right before it exploded, orders of magnitude but above what we normally see. And then you can detect them pretty easily and follow them to late times. But for the majority of them, perhaps we don't see that. And perhaps even with our current surveys, we don't see those explosions, and we're going to need to do infrared surveys or something like that to pick up on those failed collapses.
Yeah, there's been some claims of disappearing.
Yes,
massive stars.
So those remain controversial, and it's a very small number of cases. So I think the community has not yet decided whether these disappearing stars that have been reported by certain groups are truly failed collapses or not. For Wolf-Rayet stars, if those are the ones that are doing the failed collapses, those surveys are still not going to find them because those are so much lower luminosity in the optical that even those techniques are probably not going to help us determine what's going on at that. And it might if there are supergiants that undergo failed collapses, those would be detected in those surveys.
A quick follow-up if I may. Is there any correlation or anti-correlation between binarity and the disappearing stars? So in other words, if I have a star that's going to collapse and just give me a black hole, no ejector, is that more or less likely to be in a binary, or does it connect up with the sort of Gaia BH3 type observations, right?
I don't know. The binaries can do all kinds of interesting things during the stellar evolution. Whether it explodes or not at the very end is, I think, still an open question. I saw Selma put her hand up, so maybe she has some ideas.
Yeah, I would like to know the answer to your question observationally. Theoretically, there's more statements that stars stripped in binaries are much easier to explode. And so that for the same, even if you have the same core mass, the ones that went through a stripping process are more likely to make neutron stars rather than black holes and more successful explosions.
So the Gaia binaries are pretty wide, right? Yeah. Interesting.
Yeah, observationally, this is hard to address. It might be possible with large samples and determining ages by proximity to spiral arms and things like that, but that's a very indirect diagnostic. So I think the theory is going to have to drive that and make some predictions that perhaps we can try to see if they're maintained in reality.
Okay, no more questions. So let's thank Dan again. So the final talk this morning is by Seán Brennan, and that's about early warning signs, precursor activity preceding supernova.
Okay, so for those who don't know me, I'm Seán Brennan. I am a researcher here at Stockholm University, and over the past year and a half, 2 years or so, I have become very interested in this topic, which all the previous speakers have kind of alluded to, progenitors and their resulting supernova, or the activity that these progenitors show before they undergo core collapse. So as Avishay mentioned, in the preceding several years before a star explodes, something happens, the star changes, and as Dan mentioned, and K. Ryan is working on, you have some CSM around the star. So I asked the audience this general question to start off easy. What does a massive star look like before it explodes? And I mean this in the sense of on a human kind of timescale, weeks to months. As mentioned previously, probably non-hydrostatic equilibrium, the star is undergoing some type of outbursts. One concern that I have, and this relates to certain problems that we have in transient astronomy, can we trust HR diagrams or the evolutionary tracks of massive stars in this sense? If we observe a supernova, go back to historic observations and look at those progenitor detections, is that an accurate reflection of what the stellar evolution is telling us? And to exacerbate this effect, are we observing these progenitors, or is there some CSM or dust affecting these observations? And I just have two pictures here of Betelgeuse and Ida Carina, and I think this shows the disparity between how massive stars can appear. You have a very, let's call it spherically symmetric star, and then you have this very anti-symmetric system, and most likely these stars would produce very different supernovae. So, progenitor activity preceding supernova is the name of my talk, and what exactly does that mean? We have a growing sample of objects that show something at the position of the resulting supernova in the years before they explode. So there's this lovely diagram here from Andrea Pastorello, where you have your host galaxy in the center, and in 2004 there was some type of outburst at a certain position, slightly offset. This transient disappeared in 2005, and then in 2006 you had a resulting supernova, which is 06JC. So in my mind, something happened 2 years before the star exploded, giving us a signal that sometime in the future we are going to see core collapse. And we see this across different types of transients, both helium-rich, the very famous 09IP, and as well, or hydrogen-rich, excuse me, is 09IP, and helium-rich transients as well. So I won't speak specifically about any particular transient, but in the preceding 3 months before these objects go off, we are seeing some type of family of events followed by some type of core collapse supernova. The resulting light curves show some disparity as to how they evolve. You have pretty slowly rising events here, where you have this first peak followed by your supernova explosion. We also see this in 1B ends, where you have a similar evolving peak. You have these very slow, long rising events, followed by this event that reaches what we normally associate with a supernova. And then quite recently, which we'll get onto in a few slides, you almost see multiple outburst events followed by your supernova. Whether these are the same events or the same physics is going on is very difficult to address, but let's see what we can learn. So these are interacting supernovae, and for those who aren't aware, this means that the supernova ejector, or ejector of any type, it may be coming from the progenitor, interacts with some material that's surrounding the star. This is quite easy to understand conceptually, and I've just included a little diagram here of a very basic hydro simulation, where you initially start with two fluids that are next to each other, different pressure, different densities, different velocities. You allow these fluids to interact, and you have something known as a shock wave and a contact discontinuity, where I have it labeled here as your shocked CSM. And this can act as a powering source to produce a wide range of transients. This is the same diagram, except blown up. This is a very common figure that you see in interacting supernova papers. And one important feature I want to address in this talk is how do we treat the evolution of these systems. So you have your fast-moving ejector collides off your slow-moving CSM. You have your shock wave formed, as we saw on the previous slide. And then we have to take careful consideration of how these photons travel out through this region. And you have some scattering effects, which can produce these very unique, very strange profiles, which can produce very long, elongated wings, as well as asymmetries in the overall profile. And we can use these profiles with a code that I developed to actually determine the shock velocity and the opacity, or the a proxy for the density of material in front of the shock. And you can solve such equations as the shock luminosity, a very useful tool when investigating these transients. And we see this type of effect in these objects. So I have a little comparison here from Franson et al. 2022 between 09IP and a very similar object, albeit brighter, 19ZRK. In the light curve here, you can see that these objects are almost carbon copies, just one's a little bit brighter. And on the right-hand side here, this is a spectral evolution. At early times, with respect to peak, you can see our narrow features, which are common in type 2Ns, or a definition of the class. And with time, these broad electron scattering features begin to emerge. So we begin to see the interaction or the effect of the ejecta-CSM collision. And this can also be seen as bumps and wiggles in the light curve. And this tells us about what type of ejecta is colliding with what type of CSM. We can derive masses, velocities, and so on. So, as I mentioned, we're finding our observing strategy for these objects is evolving, and we are finding more and more objects where we can identify this pattern of activity early enough to actually get spectra. So this is one object we're following up at the moment, and at the bottom here you can see the spectra that we obtained. And what's fascinating is, well, it's kind of similar to 09IP. Post-peak it evolves very similarly. Fortunately, we don't capture the supernova event directly, visibility issues. But we do have spectra quite early on in the evolution. So here is one of our earlier spectrums. Now, to many, this may just look like a normal 2N. You can notice quite strikingly that our H-alpha profile has this unique feature. And then you have some features from helium and a little bit of iron too. And of course, something to note here, our supernova has likely not occurred yet. This is something that the massive star is doing in roughly a month before it explodes. And something that should strike you is your H-alpha profile is quite broad. There is a lot of energy in these events. You have very fast-moving material before core collapse has occurred. And using the models I developed, we can fit the H-alpha and H-beta line with our electron scattering code, and you can derive that there is some shock being moved through your dense CSM at around 1,000 kilometers a second, and as well a fast-moving P Cygni absorption at around 3,000 kilometers a second. Again, very high energetics and kinematics from a massive star shortly before it explodes. I should note as well, this is the same model. The only thing we are doing is changing the wavelength of the injected photons. Everything else is the same. And what is fantastic about this is if you recognize this progenitor activity early enough, you can also, in theory, time your supernova explosion and get these very early observations. So unfortunately, we didn't capture, we don't have fantastic cadence of the event itself. We do have a spectra just after it rose. You can see that our H-alpha profile has changed shape. We now have a slightly different structure. You can see this blue shoulder in the H-alpha profile, as well as the helium-1 line here shows as well. Because the supernova has gone off, and as was mentioned earlier, we do see signatures of shock breakouts seen by these high ionization lines in helium-2 and nitrogen-3. So this likely means that we are looking at a series of shell-shell collisions, and one of these shells is due to the supernova ejector being ejected at fast velocities. The previous example was a type 2N. We see this in a family of transients. We have a 1BN here, a paper that was published a couple of months ago. Different evolution to 09IP. You see a more gradual rise rather than our two peaked event A and event B light curve. Again, we were lucky here that this was initially identified as a slowly evolving nearby supernova. We got a series of spectra of this rising event. And you can see on the left-hand side here, the helium-1 5876 line shows some fantastic evolution, again showing signatures of complex CSM and electron scattering, indicating fast-moving material and shocks being formed. People familiar with the field, especially with 09IP, may remember the debate that we weren't sure if this was a supernova event or just a series of shell-shell collisions. In this example here, we do see signatures from forbidden oxygen, usually a telltale sign that nucleosynthesis has occurred and this material has been ejected into the CSM, kind of confirming that it is indeed a core collapse event. So this is quite exciting. This is an object that we're following up at the moment. You can see this black line here was when I made this plot, which is Tuesday. So this is quite a unique event. Rather than your double peak light curve or your single precursor event followed by your supernova explosion, we have these, beg your pardon, this is two events. We're just overlapping them for clarity. The events look quite similar. You do have this first series of activity here. We're not exactly sure what this is. We then identified that this object in the green and red was similar to another object we observed. We then began to follow it up quite extensively with spectra, given it by the orange markers at the top. We see signatures of shock breakouts, and then our shock signatures begin to emerge in our H-alpha profile. But then strangely, it never went up again. And this seems to be a running trend with trying to find these objects. We seem to fail to predict when the object will rise again. And at the moment, the object has gone past peak and has almost popped onto a tail. But that asks the question, if these are similar events, if core collapse has occurred and fast-moving ejecta is moving out, where exactly is core collapse on this diagram? If these two objects are the same, is this the core collapse event, and this is your fast-moving ejecta expanding out, your energy is increasing? Or typically, is this your core collapse event, and this is some precursor activity? And that means that these would be separate objects. I don't have any answers yet. I find this a very fascinating object, and time will tell what can happen. As I said, we are finding a lot of these objects thanks to ZTF. Unfortunately, ZTF can only go so faint, so we are limited by the magnitude of the survey. These square and star markers are the supernova and their precursor activity. With the ear of Rubin, we'll be able to get down to around -24, meaning that if this activity is more common than we currently think, we will be able to detect this passively with the Rubin Observatory, allowing for many, many more opportunities to study the final moments of the massive star. And I'll just leave this here. I won't go through my summary slides. I'll just touch on one point and maybe a word of caution. That when we think about the progenitor of massive stars, we need to be concerned that are we actually looking at the progenitor, or are we looking, as Avishay mentioned, the star doing something and how this has ramifications on, for example, the red supergiant problem, where we don't know exactly what massive star explodes as what supernova. I'll leave it there. Thank you.
So, other questions? Yeah.
So how often do you see the precursor events? Rates, you mean? Yes. I don't have a number for you right now. What's fascinating about this is as we find more objects, we know how to find them. Going back to ZTF, which is what I'm doing at the moment, I'm looking for nearby type 2Ns with certain characteristics, and you find that the majority of objects that should show this activity do show this activity. So that is concerning, but also exciting that this might be a common occurrence in type 2Ns, or 1BNs or supernova in general. But for an exact rate, it'll be some time before I have that number. But of course, it takes into account that there is likely 2N events that consistently don't show this. There's also events such as 20TLF, which is a type 2P that showed precursor activity, which was very different to what we've seen before. So there's likely a myriad of objects. So putting down a certain rate, we need to classify exactly what's going on first, and then figure that out.
Yeah.
Do you have an estimate for the total mass that's lost during this entire precursor phase for these different events?
Yeah, we can play around with that. With the electron scattering code, it pops out. You're looking at around 1/10 to a solar mass of material in front of the shock. So you can use that as maybe a lower limit. Of course, these are interaction-driven supernovas, so you have to have some deceleration of your ejecta, so you expect there to be a lot of material. Yeah.
Yeah, I was wondering, like in the precursor, when we have precursor spectra, like for 9IP, the initial activity was thought to be something coming from an LBV eruption. So could it be just the precursor shows like a LBV like spectra if we have spectroscopy?
Yeah, so I would assume that the common consensus at the moment is LBVs are the progenitors of two ends, but then are you looking at a LBV in the sense of a star's evolutionary time, when it's losing all its hydrogen, moving over to a Wolf-Rayet star, or is it just something that's bright blue and changing, which would also be an LBV by naming? It's unclear exactly. When you go back in your historical observations, you have one epoch where it has observations, and you assume that that's the progenitor in hydro equilibrium. Go to HR diagram and say that's it. You don't know. We don't know what the star is doing. So any progenitor detection for two ends might be slightly misleading. Oh, that's a big statement, and it's my opinion at the moment.
Okay, one more.
So can you also comment on the time scale for the precursor event? For example, you are showing some precursor event on the time scale of maybe 10 days or 1 month, but the precursor event for 06 JC actually dates back to 2 years ago before the final explosion.
So, yeah, so all the events I showed were in the preceding couple of months before the supernova exploded. But for 06 JC, it was 2 years. Again, I can't give you a scenario where this happens. It could be different events, or it could be different versions of events. Understanding how the precursor relates to the resulting supernova is what I'm working on at the moment. If I could be so bold to show one slide, this one. I didn't want to show this because it's still a work in progress. The red squares or all the colored points here are a small sample of the objects I'm looking at. We can see that there is some correlation between how bright your precursor activity gets and your resultant supernova. So whenever this event is, it is, let's say, linked or consistent with what the progenitor eventually explodes as. What would be fun is if I put 06JC on this, and then you could see if 06JC showed this activity, would we have seen it? Or would it have been too faint and fallen below detection limits? Basically, would it be somewhere down here where we wouldn't have seen it? Yeah.
Okay, any more questions? Okay, otherwise we thank.
Okay, let's start the afternoon session. So it's my pleasure now to introduce Suvi Gezari, who will give a review talk for us on tidal disruption events. And then we will have a talk by Anna Ho. These are the two talks, and then we have the afternoon coffee break. So please go ahead, Suvi.
Thank you. Well, it's wonderful to be here in Stockholm, and I'm going to be giving you an overview of tidal disruption events in the era of large surveys. So it is very appropriate for me to remind this audience that it really is an exciting time to study black holes. And in particular, there have been 2 recent Nobel Prizes in physics awarded on the study of black holes. One for the detection of black hole binary mergers via gravitational waves by LIGO, and more recently, a Nobel Prize in Physics awarded to the discovery of the supermassive black hole in the center of our own Milky Way galaxy, which has revealed itself through the orbits of individual stars in the gravitational potential. We also have other exciting probes of black holes that have emerged. Recently, there have been spectacular high-resolution radio interferometric images of the supermassive black hole in M87, as well again in our own Milky Way. And shown here, I show these orange donuts, which actually have about the same angular size on the sky. And even though they have a very different black hole mass, M87 has a black hole mass of 6.5 billion times the mass of the sun, and our Milky Way is 4 million times the mass of the sun. Because M87 is 2,000 times further away, the angular size cancels out and they look pretty much the same on the sky. What's really remarkable about these images is that the size of the event horizon that we measure with these radio images matches what you'd expect given the dynamical mass measurements of these black holes from the motions of stars in their very centers. We also have an interesting probe of free-floating black holes in our Milky Way galaxy. Recently, there was a detection using astrometric microlensing by the Hubble Space Telescope, which revealed the presence of a 7 solar mass black hole floating in our galaxy. But today, I'm going to be focusing on an entirely different and exciting probe of supermassive black holes in the centers of galaxies. And this was a theoretical concept that was introduced in the late 1980s, early 90s. This is a seminal paper by Martin Rees, which predicted the tidal disruption of stars by black holes of 1 million to 100 million solar masses in nearby galaxies. And this is a pretty succinct abstract. But what's kind of fun is this paper predicts that this should be, eventually stars should approach close enough to a central black hole to be disrupted. And that would produce a flare of radiation from the accretion of the star. And it's kind of fun that the last sentence says that stellar disruption may have interesting consequences in our own galactic center if a 1 million solar mass black hole lurks there. And of course, indeed, now we know that there is a 4 million solar mass black hole in the center of our galaxy. So while this was introduced as a theoretical consequence of black holes in the centers of galaxies, we now know that tidal disruption events are an observational reality. And I have an annual reviews article from 2021 that goes through sort of over a decade of observational evidence of tidal disruption events. Okay, so what happens when a star ventures close to a black hole? Well, the tidal forces that the star feels from the black hole can be so extreme that they literally rip apart the star. And the gas from the star is then available to be accreted onto the central black hole. So how far do you have to approach to be disrupted? Well, you can simply take the tidal force exerted on the star and set it equal to the self-gravity of the star, and you get the so-called tidal disruption radius, which scales with the radius of the star, times the ratio of the black hole mass to the stellar mass to the 1/3 power. So how close you have to get to be disrupted depends both on the mass of the central supermassive black hole as well as this type of star being disrupted. So on the top panel, I show the event horizon with a black disk and the tidal disruption radius for a solar type star in an orange circle. And you can see that the tidal disruption radius actually grows more slowly than the event horizon. That's because the event horizon scales linearly with the black hole mass and the tidal disruption radius to the 1/3 power. And in fact, if you get to very big black holes, greater than 100 million solar masses, the event horizon is actually outside of the tidal disruption radius. And so stars will be, main sequence stars would be swallowed whole before being disrupted. So tidal disruption events are really only observable for this lower mass black hole range, less than 10 to the 8 solar masses. However, we know, and we've heard a lot about the evolutionary state of stars. They can go through dramatic structural changes during their lifetime. And so the type of star also matters. So a red giant that's very extended and tenuous can be disrupted and stripped at much larger distances than a very dense system like a white dwarf. And indeed, this shows you the parameter space of where a star can be disrupted. It needs to be disrupted outside the event horizon. And This means that for solar type or main sequence stars, you can only see tidal disruption events around stars around black holes less than 10 to the 8 solar masses. And another fun consequence of this is that for very dense systems like a carbon-oxygen white dwarf, they can only be disrupted by a black hole less than 10 to the 5th solar masses. And that's because for bigger black holes, the tidal disruption radius is inside the event horizon. So if you can prove to someone that you have discovered the tidal disruption of a white dwarf, you will have smoking gun signature of an intermediate mass black hole. So tidal disruption events are very interesting for probing this lower mass black hole range, less than 10 to the 8 solar masses. And it turns out this is precisely where we know the least about the scaling relations between host galaxies and their central supermassive black holes. Here I show the famous black hole sigma relation, which is the black hole mass on the vertical axis versus the velocity dispersion of the host galaxy bulge. And we have very few measurements of black hole masses or their and how they relate to their host galaxy properties in this low mass range. The rate at which tidal disruption events occur is determined by the dynamics of the stars in the central region of the galaxy. And you can use dynamical calculations to determine how often stars will have a pericenter of their orbits that comes within the tidal disruption radius of the black hole. And the rates end up being on the order of only once every 100,000 to 1,000 years is a star unlucky enough to pass close enough to be disrupted. However, these tidal disruption event rates are very interesting for probing the central properties and dynamics of stars in the centers of galaxies. And there are interesting ways in which you could enhance the TDE rate, for example, in the presence of an eccentric nuclear disk or a binary supermassive black hole companion. So once the star is disrupted, the gas from the star, about half of it is ejected from the system at high velocities, but about half remains bound to the black hole and is available to be accreted. And this bound fraction of the debris will self-intersect, shock, and circularize to form a debris disk, which then can accrete onto the black hole. And the expected size of this circularized debris disk is about 2 times the tidal disruption radius, and that's shown with a dashed line there. So the rate at which the material falls back onto the black hole has a very well-determined t to the minus 5/3 power law with time. It also has a peak mass accretion rate that scales with the black hole mass to the 1/2 power. So that's why I have these scales up here. In principle, we could use observations of tidal disruption events to weigh massive black holes in the centers of galaxies. It's also interesting to note that the peak mass accretion rates that you get in these systems can exceed the Eddington limit by several orders of magnitude. So tidal disruption events, given their dynamic range of mass accretion rates, are excellent laboratories to study accretion physics from super Eddington to sub Eddington regimes in real time, as well as the real-time formation of an accretion disk. And as we've been hearing about using supernovae to probe the extremes of stellar evolution, tidal disruption events are also a violent way to study stars by literally ripping them apart. And so by studying tidal disruption events and their rates, we can learn about the stellar populations in the centers of galaxies. And in particular, we might even be able to use individual events to study the structure of stars. For example, the fallback rate of the material onto the black hole will depend, the timing of it will depend on the structure and size of the star. And so you're going to have very different behavior for something like a white dwarf versus a main sequence star, a red giant. And similarly, the chemical composition of these stars is very different in their chemical structures. And so in principle, with tidal disruption events, we can probe the structure and chemical properties of stars. So tidal disruption events are really exciting because they are truly multi-wavelength emitters. We now know that they have several components that our various surveys have been able to use to select them. So the most fundamental component that we think we understand the most is this soft X-ray component, which is a few times 10 or several to 10 to the 5th to 10 to the 6th Kelvin. And so this is a hot thermal continuum that's consistent with emission from the innermost accreting debris disk formed in a tidal disruption event. And these are extremely soft X-ray emitters, so almost all of the radiation is below 1 keV. However, many of our surveys, including many of the results I'll be showing today, have been picking up on a cooler component, which is this UV optical component, which has temperatures of a few times 10 to the 4 Kelvin, and is much cooler than you'd expect from the actual debris disk itself, and is likely tracing emission from material at larger radii, from around 10 to 100 times the tidal disruption radius. I'm also showing a nice schematic diagram from Krolik, which shows you the various scales that we could be probing with these different wavelength of emission. We also, interestingly, see late-time infrared emission, which from what we think is a dust echo. This is a few thousand degree Kelvin heated dust that is reprocessing the UV emission from the initial flare. We also often see radio emission, either from outflows or jets that are launched in these systems. Okay, so we truly are in an era of large surveys. On the left, I show the current all-sky surveys that we've been using to study tidal disruption events. We have eROSITA in the soft X-rays from 0.2 to 8 keV, which had completed several scans of the all-sky on a timescale of 6 months. We have, of course, the fantastic ZTF transient survey in the optical. We have an amazing census of mid-infrared transients on longer timescales with WISE. We also have some all-sky radio imaging, for example, from the VLA all-sky survey. And we're even seeing an all-sky view of particles, such as very high-energy neutrinos from IceCube. However, we are here today because this is just the beginning of this era, and we have a lot more future surveys on the horizon. We have UVEX, which is going to be performing an exciting all-sky UV survey in the far UV and near UV, which I'll talk about. We have the Rubin Observatory, which is going to have its legacy survey of space and time in the optical in the south. We're soon going to have the launch of the Roman Observatory for wide area near-infrared imaging with space-based resolution. And we're also going to have a revolution in gravitational waves beyond LIGO into LISA, as well as pulsar timing arrays. Okay, but right now we're truly in a golden age of wide field optical surveys. And of course, ZTF here is in the middle with its fantastic 47 square degree field of view. And these optical surveys have really accelerated our ability to discover tidal disruption events. In the old days, we had a trickle of about 2 TDEs per year. That's the average rate that we were discovering them. But since the advent of ZTF, we've really accelerated this to around 15 tidal disruption events per year. And we expect this to jump by a couple orders of magnitude with the various surveys I'll be describing next. Okay, well, with these optical time domain surveys, we've really come a long way in both our discovering tidal disruption events as well as characterizing them in detail. So on the left, I show one of the typical soft X-ray selected TDE candidates This is from the XMM SLU survey, where you have a few epochs of X-ray observations taken a few years apart, and you see a large amplitude outburst and a decline. You can fit it with the t to the minus 5/3 power law, but there are really only 3 points there, so it's not very constraining. And there's no real constraint on the rise time of the events. Now with optical surveys, we're using cadences of timescales of days. These have been designed to study supernovae, which many of you in the audience care about, but we can use these same data sets to discover nuclear transients and in particular tidal disruption events. And here you see one of the first well-characterized optically selected tidal disruption events from the Pan-STARRS Medium Deep Survey, where now we have multiple bands, a cadence of a few days, as well as contemporaneous UV imaging from Gal-X. So not only are we getting these detailed light curves from the optical surveys, but they're enabling the real-time discovery of these events so they can be followed up across the electromagnetic spectrum. So, of course, ZTF has played a really exciting role in our understanding of tidal disruption events and the ability to create large, statistically significant populations of them. But this hasn't been a piece of cake. We've had to work very hard to actually find tidal disruption events, and that is because while we use the established techniques of difference imaging that the supernova community does, we can't assume that every nuclear transient in the center of a galaxy is actually associated with activity with the galaxy's central massive black hole. And that is because we're clouded by a fog of pesky supernovae, which also like to explode near the centers of galaxies because there are a lot of stars near there. And so we do a really, really careful job of filtering out many of your favorite objects. And we do this by taking into account a few properties of tidal disruption events which are distinct from supernovae. One of them is, one of the most distinguishing characteristic is the color evolution. So supernovae tend to expand and cool rapidly with time. And so while they can be quite blue at early times, they will, their G-R colors, for example, will dramatically increase as you evolve with time, whereas TDEs have remarkably constant and very blue colors. So we can distinguish TDEs from most supernovae from this color and lack of color evolution. Also, the rise times and decline times of TDEs are slower than most supernovae. But as we try to explore black holes of smaller and smaller masses, we don't want to be too conservative in these cuts. But this has been, this filtering has been a great way to remove most of our contaminants. And we've been able to catch these. This is an example of a set of galaxies that we've caught. They're black holes in the act of snacking on a star. And with these optical light curves, we're really seeing a detailed view of these events, and they really seem to mimic what you'd expect from the fallback of a tidally disrupted star onto a supermassive black hole. So they have this smooth rise and power law decline that's very similar to model predictions. And just shown here is a compilation of our ZTF TDEs from the first phase of the ZTF survey. And on the left are the actual R-band data points of the light curves. And on the right are the bolometric luminosities of the light curves by taking into account their full UV optical SEDs. So we have follow-up UV imaging from SWIFT, as well as the detailed GR light curves from ZTF. And so you can get a full picture on the light curve evolution of these transients. We also have spectroscopy of our tidal disruption events. So once we filter our candidates, we follow them up for spectroscopy. And one thing that's emerged from the study of tidal disruption events is that their spectra are extremely unique. They do not look like any known AGN, and they don't look like any known supernovae. And over the years, there's now emerged 4 different classes of spectral types. and you're going to be hearing a lot more about TDE spectra later in this session. But we have some that show hydrogen and helium lines, some that show just helium-2 lines, and some that show hydrogen, helium, and Bowen fluorescence features. Sorry, there's the red class is just hydrogen lines. But what you'll also notice is that the lines are extremely broad. They have widths of 10,000 kilometers per second or more. We also have a class that we're calling TDE featureless, which just show a featureless blue continuum. But all of these TDEs are extremely blue, UV bright, and remain so for a long time. Okay, so now that we have all of these nice samples of tidal disruption events, over 50 now from ZTF, we can look for correlations or lack thereof. So I'm not going to go through all of these plots. There are a lot of things that don't seem to be correlated, but it does look like there is promising correlation between the central black hole mass, which we estimate using the velocity dispersion of the host galaxy, so that's an indirect measure, and the fallback, the decay time scale of the event. And so this is promising. If we think we can actually use tidal disruption events to weigh black holes, we really need there to be a fundamental correlation between the properties of the light curves and the mass of the central black hole. Another exciting result that has emerged, which makes us feel confident that we are actually witnessing tidal disruption events, is the evidence for a suppression of the TDE rate above 10 to the 8 solar masses, which I told you is what is expected due to capture by an event horizon. So this is showing you the rate of TDEs if you just had a Newtonian process and no black hole event horizon to capture the stars, and then what you'd expect if there is an event horizon for black holes of different spin. And indeed, observationally, already in 2017, Sjoerd van Velten pulled together 12 TDEs from many different surveys, a very inhomogeneous sample, and found that there was tentative evidence of this rate drop above 10 to the 8 solar masses. And now after ZTF1 and ZTF2, where we have a very nice spectroscopically complete sample, you can see very clearly now a robust turnover that is evidence of the event horizon. We have been doing systematic X-ray follow-up of our tidal disruption events, both with SWIFT as well as with XMM Newton. And this is showing you a gallery of our XMM Newton spectra of the optically selected ZTF TDEs. And you can see that they all show these extremely soft thermal X-ray spectra. Again, most of the photons are below 1 keV. However, while that all sounds nice, they do show dramatic variability. And there are basically two major behaviors. One is that the soft X-ray emission traces with the optical decaying flare and everything looks nice, like for example the famous Assassin 14 Li. And if you look at the UV optical to X-ray ratio, it hovers during the entire event around 1, which is what you expect for emission from an accretion disk. However, there's a whole new class of late-time brightening sources. These are sources that don't show up in the soft X-rays until hundreds of days after the initial optical flare. And their UV optical to X-ray ratios dramatically change from factors of 1,000 to order unity on the time scale of about 200 days. And we think that what we're seeing is not the delayed onset of X-ray emission, but in fact evidence of reprocessing of the soft X-ray emission, so that it's actually being suppressed. It is there, but it's being suppressed at early times, potentially due to reprocessing by, for example, an accretion disk wind. And so what's really nice here is my student Muriel Guolo has shown the spectral energy distribution of some of these events, and at different, those that had suppressed soft X-rays as well as brighter soft X-rays, and the observed UV optical and X-ray SEDs look a lot like the models for what you'd expect due to this reprocessing. Another thing that's emerged in the study and follow-up of tidal disruption events is even later time brightening in the radio. This is a beautiful compilation of radio light curves by Sendes, and you can see that for hundreds of days, many of them have no radio emission, and then suddenly brightening in the radio on the time scale of hundreds to thousands of days later. And so what is causing this radio rebrightening? It could be due to the delayed launching of outflows, change in accretion state, or perhaps we're seeing an off-axis relativistic jet. The host galaxies of tidal disruption events are quite interesting. Now that we have these large samples, we can see that TDEs seem to love to hover in host galaxies in the green valley. This is a green valley because this is actually where you see the least number of galaxies. But for some reason, our TDE hosts like to be there. And not only that, not only do they prefer galaxies that are green, and when I say green, I'm referring to the U-R color versus mass diagram, they also appear to prefer post-starburst galaxies. These are galaxies that have signatures of a quenched starburst about 1 gigayear ago. And they're also associated with post-merger systems. So we're still trying to understand what these preferences mean, but they're certainly hinting at something. And hopefully it's more interesting than just dust obscuration. Okay, well, we now have this new all-sky map in the soft X-rays from eROSITA, which also had a time domain component of on the time scale of 6 months. And again, they've been able to use this soft X-ray view of the universe to select more tidal disruption events. And again, they seem to prefer galaxies in the green valley. And we can take the soft X-ray selected TDEs with the X-ray follow-up of our optically selected TDEs and produce a very nice X-ray luminosity function. And we can use this now to make predictions for future X-ray surveys of TDEs. So hopefully you guys have heard of this new development, but in the process of looking for tidal disruption events, there's been an entirely new phenomena that's emerged in the X-rays. And these are called quasi-periodic eruptions. I show you a beautiful example from Minuti in 2022. These quasi-periodic eruptions in the soft X-rays were discovered, the first one was actually discovered in an XMM SLU survey TDE candidate, GSN 069. So they occurred at late times after the candidate TDE occurred. But you can see they are truly periodic. There's some, their period isn't completely fixed, but they really are a spectacular phenomena. And eROSITA has now discovered 4 more of these phenomena. You can see I have the recurrence time scale in hours. So these are time scales of hours. And then you have the duration on the lower plot, which is also duration of hours, as well as the bolometric luminosity of these periodic eruptions. And the best model right now for explaining these phenomena are exciting because they bring together all of my favorite acronyms. They bring together TDEs, EMRIs, and QPEs. So the idea is that you have a star in a bound orbit around a supermassive black hole. So that's our EMRI. That's our extreme mass ratio in spiral, because you have a star around a supermassive black hole. But that star in the bound orbit is actually colliding with a debris disk that formed from the tidal disruption of another star. And so this is a really exciting, and there's a recent result, I don't think it's yet on the archive, of an even stronger connection now between TDEs and QPEs. And so this is really fantastic. We're really bringing in together many aspects of the nuclear, sort of the stellar interactions with a supermassive black hole. We also have been, from both eROSITA as well as optical surveys, noticed that TDEs aren't just a one-time phenomena. We've been finding rebrightening and repeating TDEs. And so on the top, I show a spectacular example from eROSITA of a repeating soft X-ray flare, which is also detected in the UV optical. On the bottom, I show an amazing example from ASSASSIN, which is an optical all-sky survey, which again shows flaring, repeated flaring in the optical, and it also shows this in the X-rays. And in this case, we think that this is a repeating partial tidal disruption event. So you have a star on a bound orbit that's being partially disrupted and repeating. Okay, moving into the mid-infrared, WISE has also produced some exciting discoveries. We have noticed now that following a tidal disruption event, we can see a late-time mid-infrared dust echo. And you can use the ratio of the infrared emission to the observed UV emission to measure the dust covering fraction producing this dust echo. And what's really nice is you get that for TDEs, you get a covering fraction of the dust of less than 1%, whereas for AGN, which also can have flaring events, you see much higher dust covering fractions. And this is exactly what you expect given that an AGN versus a TDE have a very different dust geometry. An TDE might have some ambient dust nearby, but an AGN has a very distinct dusty torus that will have a much larger covering fraction to produce the dust echo. We can now go ahead and forget about the UV optical flare and look just for the dust echo. And that's exactly what they've done with WISE. They have their own sample of tidal disruption event candidates where there's absolutely no optical transient because it's completely dust obscured, and we just see the mid-infrared flare from WISE. And interestingly, it appears that the host galaxies of these mid-infrared selected TDE candidates are slightly different, and they may even be more massive than the optically and soft X-ray selected candidates. But it's also possible that their samples aren't completely pure, but it's definitely giving us a new window on to selecting tidal disruption events. Okay, well, just when we thought that was exciting, we've found a very intriguing association of massive black hole accreting events with very high energy ice cube neutrinos. So you may have all already heard about the association with one of the ice cube neutrinos with a known blazar, shown here, TXS something, which of course is an accreting supermassive black hole where you're looking head-on into a relativistic jet. However, more recently, we've noticed an association of ice cube neutrinos with both optically selected and mid-infrared selected nuclear flaring galaxies. Now, these are heterogeneous. Some of them are bona fide TDEs. Some of them are flaring AGN. But what's in common with both of them is they both have very strong mid-infrared dust echoes detected by WISE. And these flaring AGN and TDEs with the mid-infrared dust echoes, all these five also had ice cube neutrinos, and they're within the 90% localization region. A really spectacular aspect of these associations, and you can go through the statistics of the robustness. However, what I think is really remarkable is that in all of the cases, the neutrino is actually coincident with the peak of the dust echo and is delayed with respect to the optical flare. So originally when these were reported, it was a little bit mysterious. Why is the neutrino being detected always a couple 100 to 300 days after the optical flare? And if you then look at the timing of the mid-infrared echo, it is actually coincident with the neutrino, and implies that maybe that is a natural consequence, that to produce the high energy neutrino, you need your accelerated proton to interact with a dust infrared photon from the dust echo, then that would explain naturally the time delay, because first you have to reach the dust to produce the echo. So this is a very intriguing discovery, and we can debate on the statistics, but it may be leading us into an exciting association of high energy neutrinos with TDEs. And coming soon, there will be a new mid-infrared mission called NEO Surveyor. This is being launched in 2027. They do not care about supernovae or TDEs, but they care about protecting our planet from hazardous asteroids. But we want to remind them about the power of the mid-infrared, and that they will be detecting many interesting transients that we could potentially associate with neutrinos going forward. We're entering the golden age of infrared surveys now with the launch of Webb, which has been producing spectacular results, especially of high redshift AGN, and the Roman survey, which will be launching in a couple of years. And we argue that we think we can use these powerful infrared surveys to detect TDEs all the way out to the early universe. And I have a student, Mitchell Carman, who is looking at the detection prospects of these various surveys from Roman to JWST as well as Rubin. And we actually think that you can detect the UV bright continuum of TDEs by JWST in the mid-infrared out to redshift 10. And once you get out to these high redshifts, you can start to probe the growth history of supermassive black hole seeds. I think I'm running out of time. Okay. I just want to mention an exciting survey that's coming up in the UV, UVEX. This is going to be providing far UV and near UV imaging over the entire sky, but it'll have a wide field of view, excellent for target of opportunity follow-up of gravitational wave events, as well as broadband ultraviolet spectroscopy to follow up UV bright transients. And UVEX will be together in what I'm calling the TDE ecosystem in 2030, where we will have the UV capabilities of UVEX for cadenced all-sky imaging and UV spectroscopy, but we'll also have high cadence UV imaging with ultrasat, as well as cadenced deep optical imaging with Rubin. And so this is going to be a really exciting time to study tidal disruption events. And they will be TDE factories with the capability of discovering thousands of TDEs. Okay, I think I will finish up there, and we can discuss in the discussion what you would do with 1,000 TDEs. Thanks.
Thank you for that excellent review. Do we have questions for Suvi?
You mentioned the difficulties with all these pesky supernovae in the optical. So why isn't that a problem with the mid-infrared? How can you tell me?
Mid-infrared, the main source of contamination is going to be AGN, because you lose, with just seeing the dust echo, you lose a lot of the details of what's powering the UV emission that's powering your dust echo. So it's very hard to distinguish between a powerful AGN flare and a TDE if you just have the dust echo, but you can do things like look at the host galaxy, but I think it's always going to be a source of contamination. But supernovae, I think, are just much less luminous in the infrared. They can also produce infrared transients, but they're not going to be at the same luminosity.
But this is like you absorb photons which are emitted, right?
Yeah.
So these, I mean, supernovae are blue, right? So they
but they're not as powerful, and they're also not as blue for as long a time.
Suvi.
Yeah.
You mentioned about this relation between the neutrinos and the black hole from
Yes.
You kept saying we could argue about the statistics, but what is the significance of it?
Yeah, so the statistical significance of the associations have been reported to be 3.7 sigma. But I also saw a paper recently where they found a lower significance. So I think you know, you have to take into account the chance of, you know, if you have a certain number of detections and a certain number of background phenomena. But I think it's really intriguing that the timing of the neutrinos seem to be quite well timed with this mid-infrared echo. But there are enough neutrinos that it may be that just the spatial significance is still marginal.
Is there one of these? Do one of these plots show the significance?
The number? I mean, I have the
No. The correlation or however it is. Fine.
So the top is, these are both showing for the two studies, the ice cube localization regions on the top are the blue squares, and then the X's are the flaring AGN. And they've defined a certain threshold for infrared luminous flaring AGN.
And so the claim is that the blue is associated with the X's?
Yes, that there are 3 cases in which the X is in the blue.
Edward?
So on the topic of the use of these, is there any hope of being able to standardize them?
Oh,
if
yes.
You have different dependencies in the different wavelengths on the black hole mass and stuff like that.
Yes, so we are, the eventual goal would be to use them to probe black hole demographics. But right now, I think we're still working on our calibration. So we're definitely want to find, you know, right now we have maybe 75 or so that we can study in detail. But I think we need to continue getting their host galaxy properties. And yeah, I don't think we're confident yet to be able to use the events to weigh black holes, but certainly people are claiming to be finding, for example, lower mass black holes when they see like a faster evolving event. There are other issues with the fact that we don't actually understand where the optical emission is coming from in TDEs, so that is still a work in progress. But the soft X-ray emission, it has been argued that you could use the soft X-ray spectra to actually measure the inner radius of the black hole and actually weigh the black hole that way.
Okay, maybe. So I think we have time for one more question. I think the first hand was here, and the rest will have to be for coffee break.
Can you bring us up to date on the interpretation of this Green Valley preference? So, you know, in a sense, maybe it's not surprising that we find lots of TDEs in galaxies that have kind of been stirred up by mergers and things. But shouldn't we also be finding lots of TDEs in normal galaxies, given that they dominate the population by far? How is this interpreted?
Yes, so one idea is it could be that we're seeing the tip of the iceberg. So let's say post-merger systems, for example, have a much higher TDE rate. Then maybe we're just seeing the sort of very much amplified TDE rate from those galaxies. Another option is that dust is obscuring many of the bluer galaxies. And so we're not seeing those TDEs, although it is interesting that the mid-infrared selected TDEs do not show that. They do. There are some mid-infrared selected TDEs in star-forming galaxies, so that could be contributing. There could be a selection effect from the host galaxy obscuration. And then it could be telling us something interesting about the occupation fraction of black holes or other things. But it seems like there has to be something physically favorable to amplifying the TDE rate in these potentially post-merger galaxy systems.
Okay, I think we'll do a Q&A table later at the coffee break with Suvi, so let's thank her. Now we have Anna Hoare, who will give us the next. 5-minute warning or the 1 minute?
Sure.
Both?
Oh, I think that's a later slide. That's not the first slide.
Spoilers.
That's the first slide. Perfect, thank you. Okay, good afternoon, everyone. Thank you to the organizers for the opportunity to be here and to share with you a bit about what we've learned about fast optical transients in the last few years. My own interest in fast transients started with a question about gamma ray bursts, and so I wanted to also start my talk with those objects. Let me go forward here. So just to bring everyone onto the same page, since I know this is a broad audience, GRBs are what they sound like. They are brief, intense flashes of gamma rays, first discovered half a century ago serendipitously by satellites designed to look for clandestine nuclear tests. And now we've discovered thousands of GRBs due to satellites such as SWIFT and Fermi. These are the brightest known photon sources in the universe. We can detect them basically all the way out to the other end of the universe. And the thinking is that there are two predominant formation channels: short duration GRBs from compact object mergers and long duration GRBs from the deaths of massive stars. I'll now briefly review the traditional model for long duration GRBs. So the core of a massive star collapses and forms a compact object, and accretion or rotation powers a relativistic outflow that tunnels through the star, breaks out from the surface as a jet, and escapes into interstellar space. The gamma rays are thought to be produced by collisions between material traveling within the jet itself. To see that, we have to be looking directly down the barrel of this quite narrow, few degree wide jet. And then the jet collides with ambient gas and dust, and this produces synchrotron radiation called the afterglow, which we can observe all across the electromagnetic spectrum, from X-rays to radio waves. And as the jet decelerates and broadens, we can detect that afterglow out to large angles away from the jet axis. So that's the sort of textbook GRB picture, but there is a sort of long-standing puzzle in this field, and that is that the conditions required to both produce and detect a GRB seem kind of contrived. We infer observationally that GRBs are very rare. They only seem to occur in about 0.1% of core collapse supernovae and only seem to be associated with a special subtype of supernova called a 1C broadline supernova. And one theory is that the reason they seem so rare is that we're just seeing the extreme case of a much more prevalent phenomenon. And observationally, there have been hints that such an iceberg might exist. I'm not going to go through all of these the sort of zoo of different events, but just say for now that the physical origin of these different things and their underlying connections to the well-studied GRBs still seem quite unclear. So this is a very old question, but this is an exciting time to revisit this question for a number of reasons, that the one I'll focus on today, the theme of this meeting, is the new capabilities of optical time domain surveys. So I'd like to use the example of ZTF. ZTF uses an old telescope. The 48-inch telescope at Palomar Observatory was built in the 1940s. It spent a decade conducting an all-sky survey. And today, the same telescope, with a new camera and full robotization, can carry out that decade-long survey in just a single night. And it's this ability to map very large areas of the sky very quickly that enable us to do what we need to do to find these relativistic jetted transients not as gamma ray bursts, but instead as optical transients. And I'll illustrate what we've been finding with this figure. We saw this earlier. This is commonly used to parameterize optical transients. So you put the duration of the transient on the x-axis and the peak luminosity on the y-axis. About a decade ago, there were basically 3 major established classes of events. But then thanks to untargeted wide field surveys, the number of classes proliferated, filling in many of these so-called gaps. And what high cadence wide field surveys like ZTF are enabling us to do, and what I've been focusing on in the last few years, is push to even faster timescales and higher peak luminosities. And it's turned out that there are a lot of really interesting phenomena here. We've also, among the slower transients, been finding a lot of things related to GRBs. We've been greatly increasing the number of well-studied 1C broadline supernovae, for example. I'm not going to have time to go through all of these different things today. Instead, what I've decided to do is just focus on two of these classes of objects, beginning with the search for something called dirty fireballs. So what is a dirty fireball? Well, it's long been recognized in the GRB field that the very high energy densities in these systems imply a very large optical depth to pair production, and yet the observed gamma ray spectrum is non-thermal rather than thermal. So the way you get around this is you invoke bulk relativistic motion. So you say the material in the jet is traveling at ultra-relativistic speeds. But once you have this requirement, given the energy budget of the system, the jet has to be very, very clean. It can only entrain a very tiny amount of matter, which might be surprising since it just tunneled through this very dense environment of a star. And so it's been hypothesized in the literature that perhaps the dominant population of such things are lower Lorentz factor jets, these sort of dirty fireballs that don't produce a luminous gamma ray burst and are therefore not detected by our GRB satellites. So how can we test this hypothesis? One approach is to look for afterglows. I mentioned before the afterglow comes from the collision between the jet and the ambient medium. And the nice thing is that the jet very quickly sort of forgets its initial Lorentz factor. And so the afterglow evolution after that point is really set more by, for example, the jet energy. And so all else being equal, you might imagine that the afterglow of a dirty fireball would look very similar to the afterglow of a gamma ray burst. And so this hypothesis that they dominate the population is correct. You might expect that if you go out and you search blindly for things that look like even on-axis GRB afterglows, you might be dominated by events that have no associated detected gamma ray emission. But this is a very technically challenging problem for a couple of reasons. One reason is that afterglows are very fast transients. So this plot is showing a GRB optical afterglow light curve. The sensitivity threshold of ZTF, for example, is about 20.5. So you can see that this transient would come and go in just a few hours. So that's one challenge. And another challenge is the false positive rates. You heard from Suvi about trying to filter for TDEs. In the optical band, the sky is crowded with billions of sources varying on all timescales, of which these afterglows are just a tiny fraction. Unlike with GRBs, the gamma ray sky is quite dark. So if you see a flash of gamma rays, you can be pretty sure that it was a gamma ray burst. And so that's why, as of 2019 or so, there had only been 3 candidate discoveries of afterglows by optical surveys, 2 of which turned out to be sort of regular GRB afterglows. One event had no GRB, but also no redshift measurement, limited follow-up observations, so it wasn't really clear what that was. So we've been trying to remedy this situation using ZTF, and I'll now just walk you through the procedure that we've used to find these kinds of things. This is 1/64th of a real ZTF image. You saw the full field of view from Suvi earlier. And on a given night, ZTF takes images as part of several different surveys. Particularly relevant for this work is that we do about 1/10 of the sky multiple times per night. The process of identifying transients is fully automated through image subtraction, and importantly for us, is very fast. So from the close of the shutter following an image to the availability of these transient alert discoveries for that image is typically just about 8 minutes. Okay, so this is a special night for me because it's the first night that I found an afterglow using ZTF. This was when I was a grad student. That night, there were about 420,000 alerts. That is not, those of you working with ZTF know that some nights can be even better, upward of 500,000 alerts. These came from about 370,000 unique sources, of which I'd estimate about 140,000 are sort of real. We then apply various cuts to try to get rid of moving objects, such as asteroids. Oops, the one I just flashed by is we require 2 or more detections separated by some minimum baseline, because otherwise something can move sort of across your image. And then we apply cuts to try to remove as many flaring stars as possible. The primary false positive for this is M-dwarf flares. And then we require a certain fast temporal evolution and also red colors, because these afterglows are synchrotron emission, which in the optical band in the ZTF filters should appear red in color, and that's another way to distinguish it from stellar flares, which are hot black bodies and appear blue. And so, so that night there was one excellent candidate. It turned out to be an afterglow with no GRB, which is interesting. And since then, this has been working quite well. And I just wanted to acknowledge that many people have contributed to this effort over the years. And today, most of our afterglows are being discovered by a group of really great students at Cornell. Okay, and I wanted to give you a sense for how quickly everything unfolds once we do detect something. So this is the light curve of one of the afterglows that we found that has no associated GRB. The x-axis here is in days. So the middle of the plot here is about 1 day in the observer frame. So the optical emission we detected very early on. There were just 20 minutes between the last non-detection and the first detection. It faded very quickly. We got a spectrum at about 1 day and measured the redshift. It was about 2.5 for this object. Detected X-rays and then a detailed months-long radio light curve with the VLA. I'm just showing one frequency here, but we had quite wide frequency coverage from this event. And that's pretty typical for the afterglows that we find with ZTF. So you have to be pretty quick in this business. So today, ZTF has a number of fast transient discovery filters and projects, and altogether, we have found 17 afterglows so far. Surprisingly to me, 9 of those, if you then go back and you check, was there a GRB consistent with this time and location? The answer is yes, for about half of them. And in many cases, our ZTF discovery is the first localization of that GRB, because often these are thousands of square degree localization areas, which is kind of exciting. So I'm summarizing their light curves here. The gray, or the beige shaded background is a compilation of afterglows detected in follow-up observations of Swift GRBs, just for reference. TESS has also been finding afterglows by searching the localization regions of Swift GRBs, but then obviously by construction, they all have associated GRBs. And what you can see on the left panel is that for the most part, for our ZTF afterglows with GRBs, we're finding particularly bright afterglows, which makes sense. But then we do have a number of events with no detected GRB, which I'll talk about more in a moment. So this changes the situation quite a lot. Before ZTF, there was only one optically discovered afterglow that was followed up quickly enough for a redshift measurement, and we've increased that number by an order of magnitude. All right, so immediately, something that became very obvious is that if we select for afterglow, things that look like on-axis GRB afterglows optically, half of them turn out to have a GRB. And so that means that there is no population of events that have a kind of similar energy per solid angle to GRBs that greatly dominates the rates. So we can immediately rule that out. It also tells us something about the opening angle of the emission. So the opening angle of the material producing the GRB has to be similar to the opening angle of the emission producing the very early optical afterglow. And that's important to test because that's the basis of how people typically transform observed rates to volumetric rates. And I want to also say this is a number of people have attempted to get at this question in different ways: X-ray searches, radio searches, 1CBL, follow-up observations, and come to a kind of similar conclusion. So I think all these different avenues are converging on a picture where if you're looking for successful, energetic, relativistic jets, it turns out most of them are the GRBs that we already knew about, and that these are not, these are quite rare. But there are some puzzles here. So we do have several afterglows with no detected GRB, 5 with quite comprehensive multi-wavelength observations. Trying to understand what these were was the subject of Maggie Lee's senior thesis with me at Cornell, and she just won the physics department's Bethe Thesis Prize. And she'll go to Caltech for her PhD this fall. So I wanted to say just a little bit about what these things, what it looks like these things are, and just highlight a couple of the particularly interesting events. So this is an object that Dan Perley published earlier this year. This was an event that was found with ZTF, but then turned out to be serendipitously in a TESS field. And so there was quite high cadence coverage, which helped give a constraint on the rise time of the light curve. And by modeling that together with the detailed late time radio observations, Dan inferred a Lorentz factor that is somewhat lower than what typical GRBs might have. We have another event where we found it with ZTF, but then serendipitously the field was covered by another optical facility that resolved, again, quite a slow rise compared to typical GRBs. And again, from modeling the rise as well as our multi-wavelength afterglow observations spanning months after the burst, we're estimating somewhat lower Lorentz factors. So what are all these things? I think probably the simplest explanation is that we are detecting some afterglows that are a little bit off axis from what you would have by selecting them with a GRB detector. But there are a number of other models that have been put forward in the literature, and trying to understand these particular events is very much a work in progress. Right, so our to-do list for trying to understand what these things actually are. Absence of evidence is not evidence of absence, and I think the most direct way at this point, given the rates, to try to see whether these dirty fireballs really exist is to look for X-ray transients. So in addition to having an afterglow, a dirty fireball should have a transient that peaks in the kind of soft X-ray band. And it's really only as of this year that we have the kinds of facilities that could detect these things. You might know Einstein probe is already finding a lot of interesting soft X-ray transients. So this question can be answered. It'll be clear, I think, within the next couple of years. And then I'm interested in the UV because everything I've been talking about so far is really looking for systems that are very close to on-axis, but it's important to find the GRBs that are further off-axis to understand, for example, the angular structure of these outflows. And I think the UV is a great way to do this, and I'll say a little bit more about that later. Okay, so that brings me to the end of part one of my talk. I'm now going to switch gears and talk about a completely different class of objects that may or may not be related to gamma ray bursts. So this story started in June of 2018 when the Atlas Optical Survey discovered this transient, AT2018 COW, in a nearby galaxy. This sparked a very intensive worldwide multi-wavelength observational campaign that I'm just summarizing in this figure here. In a nutshell, it had very luminous emission, basically all across the electromagnetic spectrum, from radio all the way up to X-rays. And I would say that at this point, we don't understand any part of this multi-wavelength SED. We do think that there was some kind of central engine or active compact object involved, and that's basically because of the X-rays. So this is the X-ray light curve. It had two different phases. There was this kind of plateau phase, very high luminosity and quite a hard spectrum. And then around 20 days, it started to decline quite quickly. It showed very erratic variability, and the spectral index changed quite abruptly. And I tried all kinds of things, tried to explain this as an extension of the synchrotron spectrum from the radio, tried to explain this as inverse Compton scattering of the UV OIR photons off of the radio emitting electrons, but none of that really works. And so we and other groups were sort of forced to invoke an additional powering source. And given the timescale of the variability, I think several groups concluded that this could be sort of similar to GRBs in the sense that it's going to be some kind of massive star explosion that then resulted in a powerful outflow. But there would have to be a few quite important differences. This engine in GRBs is basically completely shrouded from the observer, but it's for some reason in these objects, we seem to be able to see much closer to it. Whereas in GRBs, the CSM tends to be fairly low density. There seem to be higher density material, kind of complicated structure in this particular object. GRBs are famously fully stripped of hydrogen and helium, but the cow had hydrogen in its spectrum. GRBs, I told you, have these ultra-relativistic speeds. These objects don't. They're more sort of trans-relativistic, 0.1 C or so. And then finally, GRBs famously have these very energetic, large nickel mass supernovae, but these objects have these very fast optical light curves, and you can use the decline of the optical light curve to put fairly stringent constraints on how much nickel mass they could have had. So I'd say that after the initial object, this was one popular picture, but there were many, many other models put forward in the literature. I won't go through these. You can look at this reference for a summary. But it was clear that we needed more objects to get to the bottom of the mystery. One of the big questions was the rates. So it was suggested early on that these might actually be quite common. And there were some very puzzling aspects of the emission. 18 Cau has turned out to have a very luminous UV source for years after the initial transient, which has been modeled as some kind of accretion disk. And the radio evolution was strange. So this is the evolution of the radio SED. And what you can see is that it started way up at high frequencies, and then it cascaded down to low frequencies. And the low frequency behavior is fairly standard. It's a broken power law going as a power law in time. But if you try to extrapolate that back, you underpredict the high frequency emission, and it was not really clear what was going on there. So these were some of the things kind of keeping me up at night, and we made a substantial effort to find more of these with ZTF. And this turns out to be a very difficult problem. It's actually harder to find these than afterglows, I would say, just because it's more difficult to distinguish them from their false positives. So the light curve here, that's often what we're working with. We have one non-detection and then maybe 2 nights of detections. And on that basis, we trigger all kinds of follow-up observations, require a host galaxy, and then bring lots of other facilities to bear to try to confirm that these have sort of similar properties to the events that we're expecting, and they're not other types of supernovae. And this has been quite successful. So in the last few years, we have found 8 events that are similar to 18 Cau in terms of their optical and radio properties. The radio properties of these things are quite different from standard supernovae, so that distinction is pretty clear. This is just a summary of some of their properties, redshift range. The X-rays seem to vary by orders of magnitude, much more so than the radio, and I think that's from beaming. They are pretty rare, so the volumetric rate, this idea earlier that they're very common is not true. The volumetric rate is closer to the GRB rate, and they do seem to occur in star-forming galaxies, and importantly are pretty much always offset from the host galaxy nucleus. And this is a compilation of the radio light curves, which I'm showing because I think it's important to know that we're sort of selecting these things as having the optical and the radio behavior together. All right, so from these 8 objects, there are a lot of things that one could talk about, and I'm just going to highlight 2 of the most puzzling aspects. One of the most puzzling aspects is the radio emission, and I want to just briefly tell you what you normally see in a supernova so you can appreciate why these objects are so weird. So typically in a supernova, you release a large amount of energy in a small volume, you accelerate electrons, you get synchrotron radiation. On the left here is the single electron spectrum. You have to make an assumption about the energy distribution of the electrons. You integrate over that and you get some net observed spectrum, so some nu to the minus alpha power law. And then there's some critical frequency where the plasma becomes optically thick to its own radiation. It's called the synchrotron self-absorption frequency, and this turns over and you get a nu to the 5 halves power law. And we see these kinds of things commonly in astronomy. Okay, so what are you trying to do observationally? You're basically trying to, typically for supernova observations, you want to constrain that synchrotron self-absorption frequency by making various assumptions. You can use that to estimate the blast wave radius, the ambient magnetic field strength, and then you can use that to estimate, for example, the shock speed and the ambient density. So that's what's very commonly done. And just want to draw your attention to this peak flux density and the product of the peak frequency and peak and time of the observation, because those are the y and x axes of a diagram that's very commonly used to parameterize radio transients. Now, for decades, centimeter wave radio observations have been used to put objects on this diagram. This is the VLA in New Mexico. And you use this to look for jets in supernovae, to study the mass loss of different kinds of stellar progenitors. And kind of the way you do this is you measure this SED, and then you can put these objects on this diagram here, where lines of constant shock speed are sort of diagonal here, and then lines of constant mass loss rate increasing to the right come up as nearly vertical. And 18 Cau shows up way up here on the upper right, and that immediately stood out as kind of peculiar. Basically, the reason it's way up there is because the peak of the radio SED is way up at 100 gigahertz or so, rather than in the conventional centimeter wave radio band. And so these are really millimeter wavelength transients. And as far as I know, so this on the far right here, you can see this detection at almost 1 terahertz with ALMA. And as far as I know, this is still basically the highest radio frequency detection of a transient to date. And so physically, why is this happening in these sources? In this kind of conventional synchrotron self-absorption picture, it's basically because you have a relatively high mass loss rate, and that's putting the peak frequency up in the millimeter band. But there are some strange features of some of these 18-count transients that actually really don't look like what you would expect from a sort of typical power law distribution of electrons. And that's led us to speculate that in some of these cases, we might actually be seeing a different population of emitting electrons. So let me explain what I mean here. I mentioned earlier that in modeling supernovae, we typically assume that the electrons are in a power law distribution of energy, which is what's being shown here with some minimum cutoff. The power law index is set by that acceleration process, and that directly predicts what that spectral index should be. And given what we think the energy index should be, that gives you a spectral index of maybe as steep as 1 or so. But in some objects, we've seen consistently a spectral index that's much steeper, of about 2, meaning that your P would be something like 4, which is challenging to explain. And then we have wondered whether it's because we're actually seeing a different distribution. So simulations of particle acceleration suggest that only some small fraction of the electrons should be in the power law, that actually most end up in what's called a relativistic Maxwellian. And in that case, you get a much steeper index. It's actually an exponential in frequency, not a power law. And people have discussed this in various contexts, but to my knowledge, not definitively seen this in an astrophysical transient. And so we've explored the possibility that you can actually describe the radio spectral energy distributions with a Maxwellian. There are a couple of things that make this appealing. One is that in one of the brightest radio loud 18-Cal objects, the yellow one on the left here, CSS 161010, they had a really beautiful new squared power law for the self-absorbed part, which is more consistent with what you'd expect from the Maxwellian electrons, not the 5/2 from the power law electrons. And then it also could help to explain why the optically thick spectral index is so steep. You can then infer shock properties in quite a different way from what we're normally doing with the power law framework. I'm not necessarily saying that this is what it is, just that one can actually explain the data with this framework. And so it's important to know which one you're actually dealing with. And so the observational test would be to see much higher frequency observations and try to see whether the transition from the Maxwellian electrons to the power law electrons can be observed. And I think that would be kind of a smoking gun signature, that's really what we're seeing here. And that would be very important because it leads you to different physical inferences about the blast wave and the environment that it's exploding in. Okay, so that's one puzzle. And then the final puzzle is some optical flaring behavior. This came up with one of the most recent one of these objects that we found. We discovered the object initially in September of 2022. And then 100 days later, we were getting optical observations to try to track the decay of the light curve. And Ping Chen he was on Magellan that night, and he got 5 3-minute G-band exposures. And so what you can see, hopefully, in these 5 images is that there's something coincident with that host galaxy that appears and disappears over a span of 15 minutes. And we couldn't really believe what we were seeing, so we got more observations and confirmed, got a second flare with the Liverpool telescope the next night. And what's amazing is that at the redshift of this galaxy, the implied luminosity is as high as the original transient event. So we got many more observations. One of the most beautiful ones was some very high cadence imaging with ultraspec. So these are 30-second cadence exposures on the Thai National Telescope. And we detected one of these flares. It lasted about 20 minutes. And you can see that it had very complicated structure. And probably we weren't even probing the shortest timescales that there were. I don't have time to say too much more. I just want to highlight some of the basic features of the flares and the observations that we got. We detected about 14 of them in the end. They turn out to be pretty rare. So the bright ones have a duty cycle as low as maybe 1% or so. And the characteristic time between them is something like a few hours. They are red in color. So we also detected a couple of them with Keck, with LRIS, which is a dichroic. So you can actually measure the color. And they're very, very clearly red. And that basically means that they have to be non-thermal. And that also means that this has to be a quite fast, almost relativistic outflow. This behavior started around 30 days after the initial transient, and it seems to have ended about 120 days after the initial transient. So this went on over and over again, probably 100 times, since we didn't detect all the flares, for about 100 days. And I don't think any such behavior has ever been seen before. Okay, so I'd say, so those are some puzzles. What are these things? I think we don't really know, but the simplest explanation is that they involve some kind of stellar mass compact object forming an accretion disk. I think two of the most popular models at this point are that it's some kind of failed supernova picture where the outflow is being powered by fallback accretion. And another popular model now is that it's sort of a merger-driven explosion. Sort of a repurposed model from something that was used in the past, actually, to try to explain GRBs. So how do we figure out what it actually is? I have a long wish list that I've put here. I think one of the most important things is to get more spectroscopy, particularly in the UV, because we still don't really know the compositions of the ejecta in these events, and that would be highly discriminating between these different models. Okay, and that brings me to the end of part 2. In the last couple of minutes, I wanted to just say, just briefly summarize and say a few words about future facilities. Just a few years ago, we really didn't have the capability to find relativistic jetted transients outside the gamma ray band, but that has completely changed. We're now doing so routinely, and that's enabled us to address both old questions in the GRB field and also help uncover completely unexpected phenomena. And as Suvi mentioned, something that's quite exciting is that in the next decade or so, the landscape of wide field high cadence surveys is really expanding across the electromagnetic spectrum. I want to say a bit about 2 of these in particular. So I'm particularly excited about the UV. Suvi already mentioned both ultrasat and UVEX, and I won't read you the different capabilities, but I think this is really critical for determining the progenitors of the sorts of transients that I've described, particularly the 18 Cal-like transients, which are incredibly luminous UV sources, both very early on and very late on in years after the original explosion. And then I also wanted to mention that we are finally getting the first wide field surveys in the millimeter and submillimeter band. And the expectations for the rates for these surveys is that they should be dominated by the classes of objects that I've described today. The Simons Observatory, for example, is being built now in Chile, and it's starting next year. It will be doing an all-sky survey from Chile with a cadence of about 3 days. The South Pole Telescope has been doing a one-day, half-day cadence survey in an area very similar to our ZTF high cadence survey. And they are already finding fairly fast transients. So they have found 4 transients so far that are quite likely to be extragalactic. The one on the left is the first transient, as far as I know, found by a millimeter survey with follow-up observations. I got some ALMA data, and that showed, it was an upper limit, but it showed that this transient faded extremely quickly. The only thing I know of that fades anywhere close to that quickly in the millimeter band is GRB afterglows, but this object had no associated detected GRB. So I think, for at least a couple of these faster events, at the moment, it seems like they're most similar to some kind of GRB afterglow-related object, but I guess the lesson to take away from our experience with optical surveys is that most likely we're also going to find things that we didn't expect to find at all. And so with that, I will leave up a plot summarizing the landscape of fast optical transients as it is today, and take any questions that you have.
Thank you so much for that. Yes, questions. Do we have any questions? Steve will start off.
Could you say something about the metallicities of the light explosion sites of these LF bots or of the host galaxies in general?
Right, we haven't really done a host galaxy study for the group at large, but at the moment, from what we have looked at, it seems like they don't have any particular, they sort of are broadly representative of star-forming galaxies. they don't seem to have it's not like GRBs or superluminous supernovae where they, but I will say our detections are quite biased because we are requiring there to be a detected host galaxy, and these are at somewhat high redshift because otherwise we have too many false positives. So we might also be biased towards finding them in somewhat more massive galaxies.
Well, thanks for your talk. I'm not sure if I remember correctly. You have mentioned at the beginning that GRBs are related to supernova type 1c, right? So I wonder, do they only happen in this type of supernova? And if yes, why is that?
Right, so I guess the way I put it is that of the long GRBs that have had that were nearby enough that we could try to spectroscopically type the associated supernova, they have all been of type 1c. The question of why that is that's an open topic, but one of the important ingredients here is that the jet has to be able to get out. And so it's thought that for these fully stripped stars, maybe that's easier given the duration of the engine, that perhaps if you have the envelope left, the jet, but when the engine stops, the jet may still be inside the star, and so it won't successfully escape.
More questions? Thank you.
Nice talk, Anna. I've got a question about basically F-bots in general and the general picture we have now. Are you totally convinced that all of them are the same physical mechanism? Or are they just sort of grouping in the same region?
Right, so I think it depends what you mean by F-bot. So when people say F-bot, I think they are often referring to the samples of objects that were put together by Pan-STARRS and the Dark Energy Survey that span a big range of absolute magnitudes. And I think from ZTF, it's pretty clear that the vast majority of those objects were type 2b supernovae and type 1bn supernovae. It's also clear that there are some things that really are quite different. And so I'd say 18 Cow and some of these other F-bots that are at the most luminous end, they do very consistently have very similar radio emission to one another. And that radio emission really doesn't look like, it's very distinctive, self-absorbed for a long time, and peaks a millimeter, that kind of stuff. And so I think the simplest explanation is that those are the same thing, but they are different from most of what people often call F-bots.
You were talking about this dirty fireball model, and you didn't find sort of evidence for that for these transients. So if, let's say, one can observationally rule out the existence of such things, do you know what that would constrain in terms of, like, I don't know, jet formation, jet propagation, or...
Yeah, I guess it would sort of mean that there's a bit of a bimodal outcome. You either make the jet, it successfully gets out, it's highly relativistic, very baryon poor, or you don't, and you don't get these sort of more baryon. So I think originally the idea was that, well, you're tunneling through the star, maybe you can entrain matter upon launch or when you're traveling through the star, and maybe that's a continuum. And it would basically mean that this process of launch and propagation prevents anything from getting in, and yeah, so I think it would tell us about the formation and propagation of these jets.
Okay. Any last question? Otherwise, let's thank Anna. I have two talks, and the first one is by Panos Charalampopoulos, who is now at Turku. Okay, maybe I didn't.
Close enough, close enough.
Spectra, so more on tidal disruption events. Take it away, Panos.
All right. Hello, everyone. I'm very happy to be here, and let me thank the organizers for this nice symposium. So apologies in advance about the fast pace of this talk. I'm going to try to convey as much as I can about the spectra of optical and UV-TDs and make a review on what we have discovered, what we have learned, and what we hope to learn in the future. Okay. Nice. All right, here we go. So Suvi made an excellent review on what TDs are, so I'm going to skip the basics. One thing I want to say that was also mentioned in her talk is that theory predicted that for supermassive black holes with masses larger than 10 in the 8, let's say, the tidal radius would be within the event horizon. Hence, the disruption would happen within the event horizon. No electromagnetic counterpart can be seen. And as we populate the sample, we indeed see this, the rate plummeting around this mass region of the supermassive black hole, which is always nice to get an extra confirmation that these nuclear flares are what we believe they are. All right, so theory predicted these in the late 80s, and the classical picture was that after various processes, the stellar debris after the disruption would start being accreted by the supermassive black hole, forming a typical thick disk of 1,000,000 Kelvin, with temperatures of 1,000,000 Kelvin. That this means it would emit in the X-rays. And in the 90s, we indeed started discovering TDs in the X-rays and some in the UV with GALEX. And then the wide field optical surveys came in, and we've seen something that we were not expecting, which is that we started discovering many optical and UV TDs. Some of them were also emitting in the X-rays, but some of them solely in the optical and UV. And this, of course, challenged our understanding of what's going on. And there were many scenarios trying to explain this. And one is that are still debated to date, I have to say. We haven't figured out what's really going on. One of them is the so-called reprocessing scenario, where due to super Eddington accretion, there are optically thick outflows forming a reprocessing envelope around the accretion, where the X-rays are reprocessed to optical and UV wavelengths. And I'm going to refer to this scenario later on, reproducing the temperatures that we detect. And with the years, this scenario was updated. It's a paper of Jane Dye, saying that there could be, that we have viewing angle dependence on what we see. That if we're looking face on, when we see the X-rays and maybe sometimes relativistic jets escaping from the funnel that you see here, looking edge on, we just see optical and UV, everything is reprocessed, and intermediate angles could reveal emission in both wavelengths. So, thanks to the wide field optical surveys, we're now discovering 15 TDs per year, and we have happily identified around 100 strong candidates so far. But yes, Suvi covered all this. So, some basic TD properties. You have radii of 10 to the 14 to 10 to the 15, temperatures of 10,000 to 50,000 Kelvin, blue continua, they're very blue. And they have broad lines always in emission of widths of tens of thousands kilometers per second. So finally, I'm focusing on the spectral properties. So in a pioneering sample study by Yair Arkavi, we understand that these broad lines are of hydrogen, so Balmer lines, and helium, this helium-2 line of 4686, very typical in TDs, and that we see also a continuum of hydrogen-rich to helium-rich events, with some events being intermediate class, so in both elements. And with the years, we kept populating our samples, we kept seeing emission lines, broad emission lines of hydrogen and helium. One thing that we discovered with the years, thanks to early spectroscopy, is that we started discovering these profiles with skewed with red extended wings and blue shifted from the rest wavelength. So a nice theoretical paper of Nathaniel Roth explained this within the reprocessing scenario as a result of an electron scattering dominated reprocessing photosphere where the profile is blue shifted due to the outflows and the red wing is due to electron scattering. And here you can see two cases that oops, okay, I didn't move on. That the early data matches indeed the model. Okay, another thing we discovered is that this was established in a paper in 2019 of Yoros Leloudas, that there is more than hydrogen and helium in the spectrum of TDs, and we started seeing these highly ionized nitrogen-3 and sometimes oxygen-3 lines, with the most prominent being this nitrogen-3 at 4640, and unfortunately next to helium-2, and another one at 4100 on top of H delta. So These lines are called Bowen lines, and they're attributed to a mechanism called Bowen fluorescence. And so these lines are showing up in the hydrogen and helium class of TDs. And this is not a surprise because in order to trigger the mechanism, you need to ionize helium-2. So you also need a source of extreme UV photons, which again is in line with the reprocessing that we're talking about. And so here's how a closer look to this heavily blended 4,000 to 5,000 angstrom region looks like. Here we're fortunate enough to be able to distinguish the two peaks of helium-2 and nitrogen-3, but in most of the cases with lower resolution spectrographs, this just appears as a blob, blended blob. So a robust way to identify nitrogen in TDs is sometimes this 4100 line, because if this was just H delta, then it might be a bit problematic. That's much stronger than H gamma. So this is a good way, and if you're not convinced, here are the spectra of a repeated TD, where the second flare happened only some months ago, and where both flares showed this booming nitrogen-3 4100 line, more prominent in the first flare, but also there in the second. There is no debate here that it's nitrogen-3. But there is more. We have also discovered a class of iron-rich TDs that show this forest of singly ironized iron lines, again in the same heavily blended region. This is reminiscent of narrow line Seyfert 1 galaxies, and this requires a thick accretion disk with highly dense medium around it. And this ties nicely with the fact that for those that we have looked, these TDs also showed strong X-ray emission, early X-ray emission, which is always soft, but still strong compared to other TDs. And to add to this diversity, another object from 2019 showed this clear double-peaked Balmer lines in the spectra, again attributed to an accretion disk seen from intermediate to large angles. It also had mild X-ray emission, faint X-ray emission. It's not the first time we see something like that, such profiles with mild X-ray emission, and not the last. You can see here, have even discovered more recently triple-peaked one. Who knows how many more in the future. And the latest addition or collection, a closest TD, most close TD to date, the 23CLX in the nucleus of an interacting liner galaxy. And I led one of the studies for this paper, and one interesting thing is on top of the broad outflow dominated H-alpha profile, we see this weird emission feature that disappears after 10 days, never to come back. And this is around 10,000 kilometers per second bluewards of the rest wavelength of H-alpha, leaving us wonder if it's a fast-moving component and why we haven't seen it in any other TDs. But for more details on the object, please go check the paper. All right. Yeah. So yeah, it's a bit more complicated than what we thought in the beginning, right? With just the hydrogen and helium picture. So how can we try to understand why we see all this diversity? First thing we should think about is modeling, right? And I can tell you there have been few attempts up to now, and that's a problem. And the ones that come in my mind are these two, actually, where they successfully reproduce the Balmer lines and the helium-2 profiles and some other qualitative features that we see in TD spectra. However, they fail in reproducing the Bowen lines and also the profile shapes. Here you can see some oddly shaped double-peaked very broad helium-2, or here helium-2 is a bit disproportionately large to H-alpha. But something we got from modeling I talked about before is that we managed to reproduce these early profiles within the reprocessing scenario attributed to outflows and electron scattering. But we definitely need to do better in modeling the spectra of TDs. So what about sample studies then? And strictly spectroscopical, I can only think of my first paper ever, first paper of my PhD, where we put a cut for events before 2019. So I really believe we can do better than first paper of a PhD student. So I'm going to talk about H-alpha, which is a very prominent line in TDs, and it's also it's not very blended, it's less blended than the other region I was talking about, so it's safer to draw conclusions from. So here I'm showing the evolution of the line weights of H alpha for the sample, but I'm color coding for these blue events are also events that show these nitrogen 3 lines I talked earlier about, and the rest with orange are those that do not. And an interesting thing we see here is that the nitrogen 3 rich TDs seem to systematically have lower velocity weights. So this is an interesting result because in a photometric population study of Stuart van Velzen, we see this nitrogen 3 rich TDs are these green squares here. They also consistently show lower, smaller blackbody radii. So if the line emitting region is also closer to the supermassive black hole, TDs, this shows that the line weights cannot be driven by the kinematics because with the velocity should be larger for the bound TDs instead of smaller. So what we suggest is that indeed, in line with the reprocessing scenario, the line weights could be set by electron scattering, and this is in line with some theoretical predictions, as well as other observables like a polarimetric sample study of Leludas et al. And here I plot the luminosity of H alpha as a function of the blackbody temperature of the TDs and the blackbody radii, and we see a correlation, like the larger the blackbody radius, the stronger H alpha is, and vice versa, or the higher the temperature, the fainter H alpha is. So I'll focus on the radius one. So this monotonic and potentially linear correlation is in line, again, with theory that, again, talking about the reprocessing scenario here, that expects that for more compact reprocessing envelopes, the emission of H alpha should fade. And another diagnostic that we wanted to check in order to maybe reproduce this, prediction is the luminosity ratio of the helium-2 line over H alpha. And we see that, for smaller radii, the ratio seems to be higher. And again, this is in line with the theoretical predictions that H alpha is self-absorbed at most of the radii, so a more compact photosphere would suppress its emission, while helium-2 is thermalized in greater depths, hence it is emitted over a larger volume. It shows that also the physical conditions could play a role in what we see. All right, and here I just want to show, yes, and this indeed, that's what I want to say, that indeed this points to a stratified TD photosphere where helium lies deeper than hydrogen and everything within this electron scattering dominated outer photosphere. Yes, so I wanted to try and see whether all these spectroscopic subclasses with their diverse and unique features could potentially fit within the viewing angle dependent scenario. So, I talked about the hydrogen and helium TDs, and some of them, show strong nitrogen 3 lines, and these are usually, we do not detect early X-rays on them, while this iron-rich class, as I said, had strong X-ray emission, and all these as a class have smaller blackbody radii, in contrast with hydrogen TDs that have larger radii. And here I divide them into subclasses, some with double peaks and mild X-ray emission, while others are normal, let's say, with no X-rays, but let's keep the hydrogen emission. So we try to explain these subclasses based on viewing angle effects. So it could be that these iron TDs, again, like narrow line Seyfert 1 galaxies, are viewed face-on through the funnel, while Bowen TDs could be viewed edge-on through, and the Bowen mechanism needs a lot of scatterings to be triggered, so they could be viewed through a tight, dense photosphere, while hydrogen TDs could be viewed from intermediate angles through a more extended photosphere, so potentially less dense, and this smaller optical depth could give rise to unique features like double peaks or mild X-ray emission, etc. And this is my last slide. Very quickly, since I'm talking about optical and UV spectra, something about the UV. We now have a handful of HST spectra. And so, I mean, one interesting thing to take away is this ratio of semi-forbidden nitrogen to semi-forbidden carbon. And the study of Young et al., they measured a lower limit for 3 early TDs of 10. So why is this important? Because in the UV, this ratio can be a powerful diagnostic of the respective abundances of these elements, because and it doesn't really depend on the specific configurations of the gas in each TD, like the optical nitrogen 3 lines. So it is suggested in this study and other studies that through this ratio we could constrain the stellar mass and the composition, of course. And this is visualized nicely in this paper of Brennan Mockler, that you see that for a, for a lower limit of 10, we can infer a lower limit for the stellar mass of the disruption, and of course that will become a very strong diagnostic to study stellar populations in the nuclei of other galaxies. So that's it from me. Thank you very much.
Thank you, Panos. So do we have any questions?
Nice talk. I've got a question about, and I might be remembering this wrong, but at least in the Hammerstein sample, there seemed to be a correlation between the black hole masses and therefore luminosity and the spectral type. And does that fit in with your viewing angle sort of selection?
Sorry, a correlation between the black hole mass and?
The spectral type. By, I guess the luminosity and the spectral type. So helium ones tended to be brighter. Whereas I think your would just be a viewing angle effect. Does that fit in? I'm not sure.
I'm trying to, because of course I'm aware of the paper and I'm trying to remember the plot. Maybe you're right. I'm sure about this connection that, the nitrogen 3 rich ones, let's say they have smaller radii and higher temperatures. But in terms of luminosity, I'm not sure whether is something. But
maybe let's chat offline, because I think
we can chat about it for sure.
Okay, more questions? Yep.
We have a lot more X-ray observations of the ZTF TDEs. Have you checked to see if your unification scheme works in terms of the spectral types of the X-ray and non-X-ray detectors?
I haven't. That's something now I think about. I forgot to say when I was finishing this slide. I want to say that that of course I would like to go and look at all the TDs after 2019 and see, because this is a this is a tentative scenario. So I would like to see if it really stands the test of time, because this was 16 TDs that we put in this whole picture. At some point I was trying to look about the H-alpha luminosities and whether it fits in, but wasn't doing the measurement myself. I was checking new papers, and they seem to indeed have this correlation with the black body radius and temperature. But lately I haven't, and of course this is a project that I would like to do, but and after 2019 we have discovered many, and it's not so easy, but I haven't checked with the X-rays, to be honest, yes.
Okay, last question over there.
Have you tried to explain featureless TDEs with the whole viewing angle thing that you've got?
No. And they're a very interesting class, but I think that, concerning nuclear transients, we still discover things that are, they do not fit so well how we think they really are. Like, for example, in this, see secondary peak sometimes, or this Assassin 15L8 thing, which was kind of featureless, they have very strong spectra. It's not, I'm not really sure how it could fit this, this picture. Okay, thanks for the question.
All right, let's thank Panos. And we welcome our last speaker for today, Achille Fiore from Frankfurt University. We'll talk about shedding light on the brightest supernovae.
Okay. Thank you. First of all, thank you to the organizer for having given me the possibility to be here today. So a few words about me. I'm a postdoctoral researcher at the Elements Cluster, which is funded by the state of Hessen, and I'm mostly working with transient and multi-messenger astrophysics. I'm a member of several observational surveys, like the IPESTO Plus survey, which observes at Entity Telescope in the City Observatory. I'm a member of the NUTS2 survey, observing at NOT Telescope in La Palma, and I'm also a member of the Padua-Asiago Supernova group, where I did my PhD in astronomy, which observes at Asiago Observatory in Italy. As you have understood from the title of this talk, I'm going to deal with this very luminous supernova, the so-called superluminous supernovae, which can be even 10 or 1,000 brighter than ordinary supernovae, whose luminosity is usually explained with the decay of the 56 nickel. But if we blindly apply this scenario to superluminous supernovae, we end up with enormous 56 nickel masses to be synthesized by a standard core collapse explosion. So possibly we are missing some ingredients, some physics to explain superluminous supernovae. Just a brief review of the very well-known from some of you observational facts. We know that superluminous supernovae, just like ordinary supernovae, are either hydrogen poor or hydrogen rich. Today I'm just dealing with hydrogen poor explosion, so the so-called superluminous supernova 1. And also after 15-30 days after maximum luminosity, a superluminous supernova 1 clearly resembles a supernova 1c, eventually in the broadline fashion, some of which are associated to long gamma ray burst. This is not a unique similarity between superluminous supernova 1 and long gamma ray burst. There's also a possible association with a superluminous supernova 1 and a long gamma ray burst, an ultra long gamma ray burst, and also the galaxy hosting superluminous supernova 1 and long gamma ray burst have some similarities. Also, photometry of superluminous supernova 1 is very interesting. The light curve of superluminous supernovae might display some bounce, some complexity, some undulation, both before and after the maximum luminosity. Here you can see the case of 2017 GZI, which has this kind of 1 magnitude wide undulation in the post-maximum phase. And also it is interesting to see that actually there's not really a canonical light curve for a superluminous supernova 1. They can evolve over a very wide range of timescales. You can see here a sample of superluminous supernova 1. The fastest one evolved can rise up to the maximum luminosity in about 20 days. The slowest one can also need, for example, 50 or even 70 or more days to rise up to the maximum luminosity. So the big question is now, how can we interpret this explosion? As many of you probably know, there are the most popular scenario considers either the contribution of a magnetar, which is left as a compact remnant from a core collapse event. This is very flexible to fit a lot of light curve shapes. Or we can consider the interaction of the supernova ejecta with surrounding circumstellar material, which at least from a photometric point of view is a nice way to explain the bumps in the light curve of superluminous supernovae. The problem is it's hard to distinguish or even to disentangle two contributions for a single superluminous supernova 1 event. Actually, as we already heard today, there's a third possibility, which is a peri-instability supernova explosion, the thermonuclear explosion of a very massive star, which completely tears apart the progenitor star and allow, due to the very high energy, to produce a massive amount of 56 nickel. However, the light curve of apparent instability-driven supernova explosion are very, very slow, as we saw the case of 2018 IBP. So they are not really easy to fit for every superluminous supernova 1 model. We have some candidates, as we heard today, but do we really need 56 nickel to explain some superluminous supernovae? Apart from the maximum luminosity, which would require a lot of nickel, as I said before, maybe some superluminous supernovae may require still a lot of nickel, but not so much nickel to power the maximum luminosity of a superluminous supernova, but still to entirely interpret the light curve evolution of a superluminous supernova, we might need some prominent contribution from 56 nickel decay. Now I'm showing to you the case of 2 superluminous supernova 1, which are currently under investigation, so these are unpublished data. You can see here the case of 2021 BNW, which I followed up with IPESTO Plus, with NUTS2, and also with Padova-Asiago, with the facilities of the Padova-Asiago supernova group. This is the multicolor photometry, and this is the pseudo-bolometric light curve, which, as you can see in the post-maximum phase, more or less on average resembled the slope of the 56 nickel cobalt decay. Alexandra Kozyreva and I are investigating a 56 nickel plus CSM interaction scenario for this superluminous supernova. Alexandra is running detailed calculation with the code Stella to model the bolometric light curve of 2021 BNW with this CSM plus 56 nickel plus CSM interaction scenario. I'm more investigating the spectral composition of 2021 BNW. And in particular, I'm investigating the helium abundance discovered in this superluminous supernova 1. This is a very preliminary plot, a plot with different models produced by Alexandra with Stella. It's a collection of models which more or less can predict an amount of about 1-2 solar masses of 56 nickel, which whose explosion interacted with 7 solar masses of which interacted with circumstellar material of about 7 solar masses. The first 2 points here do not fit with this model, so these are possibly the outcome of a pre-explosion outburst. And as I was telling you before, I'm investigating more the spectral composition of 2021 BNW, and I did this in particular thanks to a near-infrared spectrum that Ragnhild and also Linian provided me very kindly, thanks to this superluminous supernova spectroscopic follow-up program approved at CAC2 with the nearest spectrograph. So it is a near-infrared spectrum which allowed us to classify 2021 BNW as an helium-rich superluminous supernova. On the top panel, you can see the observed spectrum, and in the top right panel, you can see a zoom in the 11,000 angstroms region, which I interpreted as a composition of magnesium and helium. If I did not include helium, the fit with TARDIS, which you can see in the bottom panel, do not really reproduce that feature. The TARDIS, is a Monte Carlo tool which allows for a rapid spectral synthesis of supernovae, for those of you who don't know what TARDIS is. So the model, which is TARDIS output, is the blue trace here, and different colors correspond to different emitting ions. So you can see here calcium, magnesium, oxygen, and a bit of helium here, more or less. Now let's move to the more interesting case of 2020 TCW. Here I would really require the contribution of 56 nickel. Actually for 2021 BMW we can assume any sort of central engine, even a magnetar for example, but it was also considered in another study, so I did not investigate this scenario. But for 2020 TCW you can see, in particular in the pseudo-bolometric light curve, that this phase actually correspond to a really sharp change of slope in the light curve. So to me it really could suggest that this change of slope is something different from the mechanism powering the maximum luminosity, but still I try to, and please note that the slope here of the light curve very faithfully somehow correspond to the 56 cobalt slope. So I try to see which mass of 56 nickel could correspond to this exponential light tail, this radioactive light tail, and also to see if a single model could fit with nickel both the maximum luminosity and the exponential light decay. This is a very preliminary attempt with a very simple tool, which is TigerFit. This is not a detailed modeling as Alexandra is running for 2021 BMW. But as you can see, we require two very different nickel mass to match both the exponential decline and the maximum luminosity. For the exponential decline, we need about 0.8 solar mass, and for the peak luminosity, we need about 1.6 solar masses. So a possibility could be that actually the peak luminosity is described by a central engine here, in the case of a magnetar. So let's assume a magnetar for the moment. And then that at this point, actually, the contribution of 56 nickel decay shows up. So we possibly need, this is just an hypothesis obviously, we possibly need a physical mechanism which let the supernova explode and let produce both a magnetar and an overproduction of 56 nickel compared to standard core collapse explosions. We have already heard today about this explosion. Another possibility actually could be that a magnetorotational supernova, that a magnetorotational driven core collapse could give rise to a supernova. This, in particular, the supernova, as we also saw in during this talk of Thomas Janke, could produce much more 56 nickel than a standard core collapse explosion. I recently read a paper of the Valencia group, also mentioned this morning, by Moritz Reichert in 2023, whose model can produce up to 1 solar masses of 56 nickel. And also some models can leave a magnetar as a compact remnant. And by the way, I can say also that this kind of explosion are also a putative site which allows for our process production. This is the table I reported from the paper of Moritz Reichert. You can see here, so this is in units of 10 to the minus 2 solar masses. So this, for this model here, it corresponds more or less to 1 solar masses, which more or less agree with the very rough estimate which I did with TARDIS, and also it more or less agrees if you simply scale, for example, the light curve of 1987A up to the point in which it reaches the radioactive light tail of 2020 TCW. So my conclusions are that, as we saw before, the bright peak luminosity possibly of superluminous supernova 1 possibly requires something different from 56 nickel decay, at least for the non-peri-instability events. However, the contribution of 56 nickel could be still important to model the light curve of some superluminous supernova 1. but maybe it is not enough to explain the whole light curve of a superluminous supernova one. So, do we possibly need both a magnetar or a central engine and a huge mass of 56 nickel? And if so, how? I don't have an answer for this question. I make just a suggestion. I might be wrong. These are a bunch of my collaborators I'm working with in Frankfurt, Padova, Darmstadt, Valencia, and Heidelberg. And I'm done, so thanks for your attention.
Thank you, Achille. Questions on this? Ragnhild.
Hi, thank you for a very nice talk. I'm curious about these interaction models that you're running with Alexandra Kozareva, and you mentioned that to fit this particular object you needed the 7 solar masses of CSM. Can you comment on how much ejecta mass do you need, and do you want to speculate in the mass loss mechanism, or sort of what sort of prudential?
Okay, actually, we are very recently. Alexandra is investigating also the pulsational period instability scenario, but so far we assume the wind mass loss scenario. Also because the pulsational period instability scenario requires also a rotating moment of the progenitor. So at the moment this is not still taken into account, but we are discussing about mass loss mechanisms.
Do you remember how much ejecta was colliding with these 7 solar masses of CSM?
I guess 22 solar masses of ejecta.
Questions, Costa?
Do you need like further late time photometry for this, or like, for example, I remember in SN2014EN, so initially for like 200 days or so it tended to follow the cobalt decay slope, but then with late time photometry like past 700 days they said that it cannot be the cobalt decay but rather the magnetar spin down. So do you think?
Sorry, you are dealing with 2020 TCW, maybe?
Yeah, that's exactly it.
Okay, but let me go back. So we are here at 100 days. So you mean if this is a whole magnetar? I don't know if I correctly understood your question, but yes, it's a result that the magnetar at after I guess a while tends to reach some kind of plateau.
Yeah.
You mean
no, my point was more of like, could you do late time follow up to get the very late time decay rate so that you can for sure know out of this too which is the case?
Yes, it's absolutely a possibility, but okay, in this case we are limited to this time constraint, so we cannot jump back in fast.
Could I ask this nickel mass, 1 solar mass you had in that model, what is possible to say what makes it become so huge in that model, or it's not so easy to make such high nickel masses? So this is, you have a sort of MRI explosion,
yes, exactly.
And then you can make more nickel than in a
energy, then you can. It's more or less also what a period instability supernova. So you have more energy, so you can produce more.
Because I know in some older papers they put more energy in, but then you raise the entropy and you tend to get a lot of helium instead of. But I guess you can find a regime where you avoid that, which what they seem to have done in that model.
But it could be a possibility, but also just reporting the result of this models.
The same event, what in the light curve of the spectra is constraining the nickel mass?
Okay, but it would be interesting to have some UV spectra maybe, or some nebular spectra, what we are missing if we would be able to detect, say, I don't know, cobalt 2 lines.
No, but specifically in this event, assume I take exactly your model and put the nickel mass at 0. What will be different? Or how do you get this one solar mass in the light curve? Because looking at the light curve, it seems like the emission, the energy is dominated by the interaction.
So,
no? Am I missing something?
Sorry, you mean about these events here?
No. The one with the 7 solar masses
okay.
of
Yes, but perhaps I wasn't clear, but in this case, actually, we don't really strictly need 56 nickel. Yes, and you
the one solar mass is something that you just...
No. One solar mass is I was referring for...
okay, but over there it was that you predicted one, okay.
Okay.
Sorry.
Okay. Last question.
So in this case, in the late part of the light curve, you don't have as many photometric points as you have for the early parts of the volumetric light curve. And in particular in the Shivan, you see some wiggles. So how do you explain what you observe in the optical bands, let's say, compared to what you see in the volumetric light curve and the scenario of a nickel decay for power in this part of the light?
Yes, you are right. I don't have enough points there, so it's just, interpolation, but...
Okay.
Okay, let's thank Achille and all the speakers.